If you have ever looked at a map and noticed how the continents seem to fit together like the pieces of a broken puzzle, you have already glimpsed one of the greatest secrets the Earth has ever kept. The coastlines of South America and Africa curve into each other. The jagged edge of Antarctica tucks neatly below the southern continents. And Australia, sitting alone in the southern hemisphere, surrounded by ocean on every side, looks like it drifted away from something enormous and ancient a long time ago. Because it did. There was a time so deep in the past that human language barely has the vocabulary to describe it, when Australia did not exist as a separate place. There was no island continent, no lonely landmass floating between the Indian and Pacific Oceans, no place called the Great Southern Land. Instead, Australia was part of something vast, something that geologists would eventually name Pangaea, a supercontinent that contained nearly all the land on Earth gathered into a single enormous body. And within that supercontinent, within that ancient unified world, the piece of land that would one day become Australia was quietly doing something extraordinary. It was building itself, layer by layer, collision by collision, river delta by river delta. If you're listening to this to sleep, let these words carry you into deep time. Let the slow drift of continents be the rhythm that guides you down. There is nothing to hold on to here, nothing urgent or pressing, only the vast, unhurried patience of the earth, rearranging itself across hundreds of millions of years, building the land you know, one impossible slow movement at a time. Subscribe if this kind of story is what you come here for, because there are more of them waiting. Number 1, the world before the world. Before we can understand what Australia was doing during Pangaea, we need to understand what the Earth looked like before Pangaea existed. Because Pangaea was not the beginning. It was not the first time the continents had gathered together, and it was not even close to the first chapter in the story of Australian rock. The Earth is approximately 4.5 billion years old. Pangaea, the supercontinent that most people have heard of, existed between roughly 335 million years ago and 200 million years ago. That means that before Pangaea, the Earth had already been spinning through space for more than 4 billion years, building and breaking and rebuilding its surface in ways that most of us never learn about. The portion of ancient rock that would eventually become the core of Australia is among the oldest material on the surface of the planet. Deep in what is now the Pilbara region of Western Australia, there are rocks that have been dated to more than 3.5 billion years old. In the Jack Hills of the same region, geologists have found individual crystals of a mineral called zircon that are 4.4 billion years old, making them the oldest known material of terrestrial origin on Earth. Think about that for a moment. When those crystals formed, the moon had only recently separated from the Earth, following a catastrophic collision with another planetary body. The oceans were still in their infancy. The atmosphere contained almost no oxygen. Life itself had not yet begun. And yet, the material that would one day become Australian rock was already there, already crystallizing, already beginning the slow process of accumulation that would one day produce a continent. The early Earth was a far more violent place than the planet we live on now. The surface was geologically hyperactive, with magma rising through the crust in enormous plumes, volcanic eruptions on a scale we have never witnessed in recorded history, and a constant bombardment from space as the solar system was still clearing out the debris left over from its formation. In this chaotic environment, the first stable cratons, the ancient nuclei around which continents would eventually grow, were beginning to form. A craton is a piece of ancient, stable continental crust that has survived for billions of years without being significantly deformed or altered. The cratons are the true old bones of the continents, the pieces that have persisted through the building and breaking of every supercontinent, through ice ages and mass extinctions, and the slow drift across every latitude the planet has to offer. Australia has some of the largest and most ancient cratons on Earth, and it is these cratons that give the continent its geological character, its flatness, its stability, and its extraordinary age. The Western Craton, which covers a large portion of what is now Western Australia, began forming more than 3 billion years ago, over hundreds of millions of years. It grew through a process called accretion, where smaller pieces of crust collided and welded themselves to its edges, growing the stable core outward in all directions. Volcanic island chains formed in ancient oceans and were then swept against the craton by the movement of tectonic plates, adding new material to the growing landmass. Sedimentary basins filled with the remains of ancient seas and rivers, compressing over millions of years into the layered rock sequences that geologists study today. All of this happened long before Pangaea, long before the Carboniferous period when the continents began their great gathering, long before the Permian and Triassic when the supercontinent reached its fullest extent. The rocks of Australia carry a memory that stretches back to the very origins of life on Earth, and perhaps even before life began. If you let your mind drift back that far, back past the dinosaurs, past the first fish, past the first complex cells, all the way back to a planet without oxygen in its air or life in its seas, you arrive at the place where this story begins. A world of rock and heat and slow accumulation, building the foundations of a continent that would one day sit alone surrounded by ocean as the last surviving fragment of an ancient southern world. Number 2. The name we use and what it really means. The word Pangaea comes from ancient Greek and it means something beautifully simple. Pan means all or entire. Gaia means earth. All earth. The entire earth gathered into one. When geologists and earth scientists use the word Pangaea, they are referring to the most recent supercontinent, the one that existed from roughly 335 million years ago until it began to break apart around 200 million years ago. But the concept of Pangaea, the idea that the continents had once been joined, was not always accepted by science. For most of human history, the idea that continents could move at all would have seemed absurd. The ground beneath our feet feels solid and immovable. Mountains look permanent. The shape of the coastline seems fixed and eternal. How could anyone believe that these enormous masses of rock had once been connected and had slowly drifted apart over millions of years? The man most often credited with developing the theory of continental drift was a German geologist and meteorologist named Alfred Wegener. In 1912, Wegener presented a radical idea that all the continents had once been joined in a single supercontinent, which he called Urkontinent, meaning original continent, though the name Pangaea eventually came to be used. Wegener pointed to the matching coastlines, the identical rock formations found on opposite sides of the Atlantic Ocean, the fossils of the same species found in places that are now separated by thousands of miles of open sea. The scientific establishment largely rejected Wegener's ideas during his lifetime. He died in 1930 on an expedition to Greenland, without seeing his theory accepted. The problem was not the evidence, which was compelling. The problem was mechanism. Wegener could not explain how continents, which are made of rock, could possibly move through the oceanic crust, which is also made of rock. It seemed physically impossible. It was not until the 1950s and 1960s, when oceanographers began mapping the floor of the ocean in detail, that the mechanism became clear. The ocean floor is not static. It is constantly being created at mid-ocean ridges, where magma wells up from the mantle and solidifies into new rock, and constantly being destroyed at subduction zones, where older oceanic crust dives back into the mantle. This process, called plate tectonics, is what moves the continents. They are not plowing through oceanic crust. They are riding on top of enormous plates of lithosphere that are in constant, if imperceptibly slow motion. Once plate tectonics was understood, the history of Pangaea and all the supercontinents that came before it could be reconstructed with increasing precision. Geologists could look at the ages and compositions of rocks, the directions of ancient magnetic fields preserved in volcanic material, the patterns of mountain belts and ocean basins, and work backward through time to reconstruct where each piece of crust had been hundreds of millions of years ago. And what they found, when they traced the piece of crust that would become Australia back through time, was a journey of extraordinary length and complexity. Australia's rocks carry the signature of multiple supercontinent cycles, multiple collisions and rifting events, multiple periods of being part of enormous landmasses, and then being isolated once again. The story of Australia during Pangaea is really the story of Australia during several supercontinents, each one the chapter of a larger epic that stretches back billions of years. As you settle into sleep, let this be the ground beneath you. Old rock, patient rock. Rock that has seen ice ages and fire ages, that has sat on the equator and drifted toward the poles, that has been buried under kilometers of ocean sediment, and then lifted by collision into mountain ranges that time has slowly worn to nothing. The land beneath you is not young, it is not static. It is the product of a journey so long that it dwarfs everything human civilization has ever done. Number 3, Gondwana, the mother of the South. Before we get to Pangaea specifically, we need to spend some time with Gondwana, because Gondwana is the chapter of this story that Australia is most closely associated with, and the one whose legacy is most visible in Australian nature today. Gondwana was a supercontinent that formed about 500 million years ago, during the late Cambrian and early Ordovician periods. It was enormous, comprising what would eventually become Africa, South America, Antarctica, Australia, India, New Zealand, Arabia, and various smaller landmasses. For roughly 300 million years, these landmasses were welded together into a single enormous continent that dominated the southern hemisphere of the Earth. The name Gondwana comes from a region in central India where geologists first identified the distinctive geological formation associated with this ancient supercontinent. The Gondwana Formation, as it is called, contains rocks and fossils that are found across the southern continents, a shared geological signature that tells the story of a shared history. Australia's participation in Gondwana was not passive. The eastern portion of the Australian continent was actively being built during the Gondwana period, through a series of collisions and accretion events collectively known as the Tasmanida orogeny, or the Tasman orogenic belt. While the ancient western cratons had been stable for billions of years, the eastern margin of the Proto-Australian crust was a dynamic and geologically active place, where volcanic island arcs were being welded to the growing continent. Deep ocean sediments were being folded and compressed into mountain ranges, and the overall size of the landmass was increasing. The mountains that formed during this period no longer exist in their original form. They have been worn down by hundreds of millions of years of erosion to the gentle ridges and low ranges that now form the eastern highland spine of Australia. But the rock sequences they left behind, the compressed and folded sedimentary sequences that geologists find in New South Wales, Queensland, and Victoria, tell the story of a period of enormous geological activity that shaped the fundamental structure of the continent. During the early period of Gondwana, Australia was positioned in a very different part of the world than it is today. The southern part of the combined landmass sat close to the South Pole, and Australia's portion of Gondwana experienced conditions that would be completely unrecognizable today. There were glaciations, periods of intense cold when ice sheets advanced across what is now the warm red interior of the continent. There were deep, cold oceans where the Great Barrier Reef now stands. There were forests of a kind that no longer exists anywhere on Earth, composed of species that evolved in isolation on the southern supercontinent and whose descendants still survive today in modified forms. The plants of Gondwana are one of the most extraordinary legacies of Australia's participation in this ancient supercontinent. The Gondwana flora included many species of trees and plants that are still found across the southern continents today, clear evidence of their shared ancient origin. The distinctive southern beaches of the genus Nothofagus are found in South America, Australia, New Zealand, and New Guinea, islands of distribution that only make sense if you know that all these landmasses were once connected. The ancient cycads, the tree ferns, the podocarp conifers, all of these plant groups preserve in their living diversity the outlines of a botanical world that Gondwana created, and that continental drift then distributed across the southern hemisphere. Australia's extraordinary biodiversity, the fact that roughly 80% of its flora and fauna are found nowhere else on Earth, is in large part the product of its long participation in Gondwana, and then its long isolation after Gondwana broke apart. The ancestors of today's uniquely Australian species had time, in the isolation provided by the surrounding oceans, to evolve along their own distinctive pathways. The marsupials, the eucalypts, the wattles, the extraordinary diversity of birds, all of this biological uniqueness has its roots in the ancient world of Gondwana. Number 4. When Pangea was assembling. Now we arrive at the specific chapter of the story that gives this video its title. What was Australia doing during Pangea? Pangaea, as a unified supercontinent, began to form around 335 million years ago, during the Carboniferous period. The assembly of Pangaea was not a single event. It was the result of a long series of continental collisions that gradually brought together the various pieces of the Earth's crust into a single enormous landmass. The northern continents, a group called Laurasia, comprising what would become North America, Europe, and Asia, collided with the southern supercontinent Gondwana, which included Australia, to form Pangea. At the time of this collision and assembly, Australia was still firmly embedded in Gondwana. It was not a separate continent. It was a portion of an enormous landmass that stretched from what is now the Antarctic coast up through Africa and across to South America, with Australia occupying roughly the position of the Indian Ocean in today's geography, adjacent to Antarctica and India. During the Carboniferous and Permian periods, which is to say roughly 360 million to 250 million years ago, Australia experienced some of the most dramatic climatic conditions in its long history. The southern portion of Gondwana, including Australia's territory, was positioned close to the South Pole, and enormous ice sheets advanced across the continent. This glaciation left behind distinctive sedimentary deposits called glacial tillites, layers of mixed rock debris that were dumped by glaciers as they advanced and retreated. These glacial deposits from the Permian period are found across Australia today, evidence of a time when the land that is now one of the hottest and driest continents on Earth was covered in ice. In some places, geologists have found striated bedrock, rock surfaces that were scraped and scratched by the advance of ancient glaciers, preserving in stone the direction and movement of ice sheets that melted more than 250 million years ago. The Carboniferous period in particular was a time of remarkable biological productivity in the portions of Pangaea that were warm and humid. In the tropical and subtropical zones of the supercontinent, vast forests of giant club mosses, horsetails, and ancient tree ferns covered the land. These forests, growing in swampy lowlands, produced enormous quantities of organic material that accumulated in the wet soil and was eventually buried and compressed over millions of years into the coal deposits that fueled the Industrial Revolution. The word Carboniferous itself means coal-bearing, and the coal seams of this age are found on every continent that was part of Pangaea. Australia has significant coal deposits of Permian age, formed not during the peak of tropical productivity in the northern parts of Pangaea, but during the subsequent warming as the southern glaciations retreated. As the ice sheets melted and the climate of the Australian portion of Gondwana warmed, swampy forests developed, and their accumulated organic matter was buried and compressed into the coal that lies beneath much of eastern Queensland and New South Wales today. The Permian period also saw the development of one of the most characteristic plant communities of Gondwana, a flora dominated by a seed fern called Glossopteris. This plant, now extinct, grew in enormous quantities across the southern supercontinent, and its distinctive tongue-shaped leaves are found as fossils in rocks of Permian age across Australia, Antarctica, Africa, South America, and India. The discovery of Glossopteris fossils in Antarctica by Robert Falcon Scott's ill-fated expedition to the South Pole in 1912 was actually part of the evidence that Wegener had used to support his theory of continental drift, because no seed fern could have evolved identically on continents that were separated by thousands of miles of ocean. Number 5, the geography of an ancient Australia. Let us try to picture, as clearly as we can, what the portion of land that would become Australia actually looked like during the height of Pangaea. The first thing to understand is that the land itself was in a different position relative to the poles and equator. During the early Permian period, roughly 280 million years ago, the Australian portion of Gondwana was positioned at approximately 60 to 70 degrees south latitude. For comparison, that is roughly the latitude of the Antarctic Peninsula today. The climate was cold, glaciated in places, and dramatically different from the warm subtropical conditions that characterize most of modern Australia. The landmass that would become Australia was larger in some ways, and smaller in others than the continent we know. The ancient cratons of the west and north were broadly in positions similar to where they are today relative to each other, but the overall shape of the coastlines was completely different. Much of what is now the continental shelf was dry land. The interior of the continent, which is now dominated by vast flat plains and the remnants of ancient mountain ranges, was a different kind of landscape altogether. During the glacial periods of the Permian, the landscape of Proto-Australia would have resembled parts of modern Antarctica or northern Canada. Ice sheets covered significant portions of the landmass, and around their edges, glacial outwash plains spread outward, deposits of rock debris carried by meltwater streams and spread across flat lowland areas. The rivers of this cold landscape were powerful and erosive, cutting through the ancient rock of the cratons and carrying sediment outward toward the distant coasts. As the Permian progressed and the glaciations began to retreat, the climate of the Australian region began to warm. Tundra-like vegetation colonized the areas newly exposed by the retreating ice. Then, as conditions continued to improve, the Glossopteris forest spread across the warming landscape, creating a green cover over rock that had been bare for millions of years. These forests, growing in cool but increasingly temperate conditions, were very different from the tropical coal swamps of the northern parts of Pangaea, but they were enormously productive, and their remains form the basis of Australia's coal wealth today. The interior of the Proto-Australian landmass during this period contained significant ancient mountain ranges, now long since worn away. The Petermann Ranges of Central Australia, the Musgrave Ranges, the McDonnell Ranges, all of these ancient rock formations are the eroded remnants of much higher mountains that existed during the earlier Gondwana period. By the time of Pangaea's peak, these mountains had already been substantially reduced by erosion, but they were still significant features of the landscape, creating elevated terrain in the interior of the continent and influencing patterns of rainfall and river drainage. The rivers of ancient Australia flowed outward from these central highlands in patterns that are sometimes similar to and sometimes completely different from the river systems we know today. In some parts of the continent, the ancient drainage patterns can still be traced in the landscape, preserved as dry valleys and ancient watercourses that now lie in desert country. In other places, subsequent geological events have completely rearranged the drainage patterns, creating rivers that flow in directions the ancient landscape would not have predicted. Around the margins of the landmass, ancient seas advanced and retreated multiple times during the Permian and Triassic periods. Shallow epicontinental seas, seas that covered the edges of the continent with relatively shallow water, deposited enormous thicknesses of sedimentary rock that now form the foundations of significant portions of Australia. The Permian-Bowen Basin of Queensland, now one of the most important coal-producing regions on Earth, was formed in one such shallow marine and deltaic environment, where rivers draining the ancient highlands deposited their loads of sediment into the sea. If you could somehow travel back in time to the Australian portion of Pangea, the most striking thing would probably be the silence. No birds, because birds would not evolve until much later. No flowering plants, because the flowering revolution in plant evolution was still more than 100 million years in the future. No grass, which would not appear until after the dinosaurs were gone. The landscape would be dominated by the ancient Glossopteris forests, by ferns and horsetails and primitive conifers, and by the sound of wind and water on a land that was slowly warming after the cold of the Permian glaciation. The animals of this landscape were the ancestors of the animals we know today, but they were profoundly different. The Permian period was the age of the therapsids, the mammal-like reptiles that would eventually give rise to the mammals. These creatures, ranging in size from small mouse-like insectivores to large, powerful predators the size of modern wolves, were the dominant land vertebrates of the time. Some of them may have been warm-blooded, or at least had metabolisms more advanced than those of their cold-blooded ancestors. Some may have had primitive hair or fur. They were, in a sense, the halfway point between the reptiles that had dominated the land before them, and the mammals that would come to dominate it after. Number 6. The Great Dying and what it meant for ancient Australia. At the end of the Permian period, roughly 252 million years ago, the Earth experienced the largest mass extinction in its history. This event, known to paleontologists as the Permian-Triassic extinction event, or informally as the Great Dying, killed an estimated 96% of all marine species and 70% of all terrestrial vertebrate species. It was, without question, the closest life on Earth has ever come to complete annihilation. The causes of the Great Dying are still debated among scientists, but the most widely accepted explanation involves the eruption of the Siberian Traps, one of the largest volcanic provinces ever to have existed on Earth. Over a period of perhaps 1 to 2 million years, vast quantities of basaltic lava poured out across what is now Siberia, covering an area the size of Europe to depths of several kilometers. The eruptions released enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere, triggering a cascade of environmental catastrophes: rapid global warming, ocean acidification, the collapse of the marine food chain, and widespread oxygen depletion in both marine and terrestrial environments. For the Australian portion of Gondwana, the Great Dying was a catastrophic event. The Glossopteris forests, which had covered much of the landscape, collapsed almost entirely. The therapsid faunas that had been building in diversity for tens of millions of years were decimated. The marine environments around the margins of the continent, teeming with the corals, brachiopods, and cephalopods of the Permian Sea, were essentially emptied as ocean chemistry changed in ways that most organisms could not survive. The Permian-Triassic boundary in Australian rock is often marked by a distinctive layer, a zone of barren or nearly barren sediment, where the normal fossil record simply disappears. Below this layer, the richness of Permian life. Above it, silence or nearly so. And then the slow, uncertain beginnings of recovery. The recovery of life after the Great Dying was a process that took roughly 5 to 10 million years to produce ecosystems of comparable diversity to those that had been lost. In this recovery period, the survivors of the extinction had an opportunity to diversify and fill ecological roles that had been vacated. Some of the animal lineages that would eventually produce the dominant creatures of the Mesozoic era, the dinosaurs and their relatives, originated in this period of recovery from the Great Dying. For the piece of land that would become Australia, the recovery from the Great Dying marked the transition from the Permian world of Glossopteris and Therapsids to the Triassic world of the earliest dinosaurs and the plant communities that would characterize the Mesozoic. The landscape did not change overnight. Recovery was slow and uneven, with some groups recovering more quickly than others, some regions recovering more fully than others, and the overall composition of ecosystems shifting gradually over millions of years as the survivors of the extinction diversified and new ecological relationships were established. Number 7. The Triassic and the first chapter of breakup. The Triassic period, which lasted from approximately 252 million years ago to 201 million years ago, was in many ways the high water mark of Pangaea. By the beginning of the Triassic, the supercontinent was fully assembled, stretching from pole to pole in a single continuous landmass. The interior of Pangaea was characterized by extreme continental conditions, hot and dry in the summer, cold in the winter, with monsoon rains along the coasts, but profound aridity in the depths of the interior, far from any moderating ocean influence. For the Australian portion of this supercontinent, the Triassic brought significant changes. The climate was warming and drying compared to the cold and glaciated Permian. The Glossopteris forests had been replaced by new plant communities dominated by different kinds of seed plants, including the first primitive conifer forests that were beginning to spread across the recovering landscapes. The Therapsids, though decimated by the Great Dying, were still present and beginning to diversify once more, evolving toward the forms that would eventually produce the first true mammals. But even as Pangaea was at its most complete, the forces that would eventually tear it apart were already at work beneath the surface. The heat generated by the Earth's interior, unable to escape efficiently through the thick lid of continental crust that covered so much of the planet's surface, was building up in hotspots beneath the supercontinent, creating instabilities that would eventually cause the lithosphere to fracture and rift apart. The breakup of Pangaea began in the late Triassic and early Jurassic periods, starting in the north with the opening of the Central Atlantic Ocean as North America began to separate from Africa. But the southern portion of the supercontinent, the Gondwana portion that included Australia, remained intact for much longer. Gondwana began to break apart in a more complex and prolonged process that would eventually separate Australia from Antarctica, India from Africa, and all the southern continents from each other. The first signs of Gondwana's impending breakup, visible in the Australian geological record, appear in the Triassic and Jurassic in the form of volcanic activity and rifting along what would become the future margins of the continent. As the lithosphere stretched and fractured, magma welled up along the rift zones, creating volcanic provinces and filling the developing rift basins with both volcanic rock and sedimentary deposits. Number 8. The Jurassic landscape of Proto-Australia. The Jurassic period, spanning from approximately 201 million to 145 million years ago, is often associated in the popular imagination with the great dinosaurs, the long-necked sauropods, the fearsome theropods, the plated stegosaurs. And indeed, dinosaurs were the dominant large-land animals of the Jurassic period, and their fossils are found on every continent, including Australia. For the Australian portion of Gondwana during the Jurassic, this was a period of significant geological and biological change. The climate had continued to warm and shift from the cold Permian conditions, and the landscape was increasingly covered by forests of conifers, cycads, and tree ferns, a lush green world very different from the sparse Permian Glossopteris forests. The interior of Gondwana, which had been cold and glaciated in the Permian, was now warmer and wetter in many areas, supporting rich forest ecosystems. Australian Jurassic dinosaur fossils have been found in several locations, primarily in Queensland and Victoria, and they provide tantalizing glimpses of the creatures that walked the ancient landscape. One of the most significant fossil sites is in the Toolbuck Formation and related Jurassic Cretaceous sequences of Queensland, where the remains of sauropod dinosaurs have been found. These long-necked plant eaters, some of them among the largest animals ever to walk the earth, were browsing the ancient forests of Proto-Australia during the Jurassic. But perhaps the most remarkable aspect of Australia's Jurassic history is not its dinosaurs, but the condition of its surrounding seas. During the Jurassic and into the Cretaceous, vast, shallow epicontinental seas covered much of what is now the interior of Australia. The Great Artesian Basin, one of the largest groundwater reservoirs on Earth, sits beneath a large portion of inland Australia, and the layers of sedimentary rock that contain its water were deposited largely in these ancient Jurassic and Cretaceous inland seas. These seas, shallow and warm, teeming with marine life, were home to extraordinary creatures, plesiosaurs, long-necked marine reptiles that are sometimes popularly but incorrectly associated with sea serpent mythology, swam in the shallow inland waters of Proto-Australia, ichthyosaurs, dolphin-like marine reptiles, hunted fish in the ancient seas, giant ammonites, coiled shell-bearing cephalopods related to the modern nautilus, drifted through the warm water. The fossil record of these seas, preserved in the rocks of the Eromanga Basin and the Winton Formation, is one of the most remarkable collections of Mesozoic marine and semi-marine fossils in the world. The rivers that flowed from the ancient highlands into these inland seas carried enormous loads of sediment, building up deltas and floodplains that are preserved in the Winton Formation of Queensland, one of the most productive dinosaur fossil sites in Australia. It is here that some of Australia's most significant dinosaur discoveries have been made, including the enormous sauropod Australotitan cooperensis, described in 2021 as possibly the largest dinosaur ever found in Australia, with an estimated length of perhaps 30 meters. Number 9. The Cretaceous and the beginning of isolation. The Cretaceous period, from approximately 145 million to 66 million years ago, was in many ways the most important period in the story of Australia's separation from the rest of the world. It was during the Cretaceous that the rifting of Gondwana accelerated, as India separated from the combined Australia-Antarctica landmass and began its dramatic northward journey toward collision with Asia. Australia itself remained attached to Antarctica throughout the Cretaceous. The two landmasses were still welded together along what is now the southern margin of Australia and the northern margin of Antarctica, with no open ocean between them. But the rift that would eventually separate them was already developing, and the first deep ocean basins were beginning to open at the edges of the growing continental margin. The Cretaceous was also the period during which the global sea level was at its highest in the past several hundred million years. The warm Cretaceous climate, driven by high concentrations of atmospheric carbon dioxide, had melted any polar ice that existed and caused the oceans to expand thermally. The result was that shallow seas covered much more of the continents than they do today, and Australia's interior remained largely flooded by the shallow Eromanga Sea for much of the Cretaceous period. This Cretaceous inland sea at its peak may have covered as much as a third of the Australian continent. It was connected to the ocean to the north and south, creating a seaway that effectively divided the continent into eastern and western portions. The creatures that lived in and around this sea left behind an extraordinary fossil record that Australian paleontologists have been working to uncover for decades. The Cretaceous was also the period that saw the great diversification of flowering plants, the angiosperms, which would eventually come to dominate the world's vegetation. Early angiosperms appeared in the Cretaceous and spread rapidly, diversifying into an enormous variety of forms that replaced the ancient gymnosperm-dominated forests in many parts of the world. The arrival of flowering plants transformed ecosystems, creating new ecological opportunities for pollinators and fruit-eating animals, and setting the stage for the extraordinary diversity of flowering plant species we see today. In Australia, the earliest evidence of flowering plants appears in Cretaceous sediments, and the subsequent evolution of the Australian flowering plant flora, in the isolation that would follow Gondwana's final breakup, would produce the extraordinary diversity of eucalypts, wattles, banksias, grevilleas, and other uniquely Australian plant families that dominate the modern landscape. Number 10. The Age of Polar Forests. One of the most remarkable and counterintuitive chapters in Australia's geological history involves a period when part of what is now Australia lay within the Antarctic Circle. During the early Cretaceous, roughly 110 to 115 million years ago, the southeastern portion of the Proto-Australian continent was positioned at approximately 70 to 80 degrees south latitude, well within what we today call the Antarctic region. This might seem to suggest that the area was frozen and barren, as Antarctica is today. But the Cretaceous world was dramatically warmer than our own. The global average temperature was significantly higher than today, and even the polar regions, while cold by the standards of the tropics, were not covered in permanent ice. Instead, the polar regions of the Cretaceous supported forests, dense, productive forests that grew through the extraordinary challenge of polar seasons, months of continuous daylight in the summer, and months of complete darkness in the winter. The polar forests of Cretaceous Australia are one of the most extraordinary discoveries of Australian paleontology. The Otway and Strzelecki ranges of Victoria and the area around what is now the coastline of southeastern Australia were once within the rift valley that was developing between Australia and Antarctica as the two land masses slowly began to separate. The fossils found in the rocks of these ranges, preserved in sediments deposited along the ancient Rift Valley floor, reveal a world that completely upends our assumptions about ancient climates. The Dinosaur Cove site in Victoria, excavated by Thomas and Patricia Rich beginning in the 1970s and continuing for decades, has yielded fossils of dinosaurs that lived at polar latitudes, enduring months of winter darkness each year. These polar dinosaurs, which included small hypsilophodontid ornithopods and possibly other groups, must have had physiological and behavioral adaptations for surviving the polar winter that we do not fully understand. Some may have migrated to warmer latitudes during the winter, following the available food. Others may have remained in the polar forest year-round, finding food even in the darkness and cold of the southern winter. The diversity of dinosaurs found at Dinosaur Cove and related sites in Victoria indicates that these polar forests were genuinely productive ecosystems, not marginal environments barely capable of supporting life. The fossil record includes not just dinosaurs, but also early mammals, pterosaurs, turtles, fish, and a rich invertebrate fauna, all living at latitudes that today support nothing but permanent ice. The existence of these polar forests tells us something important about the relationship between continental position and climate. The position of Australia within the Antarctic Circle during the early Cretaceous should, under modern climate conditions, have produced an environment similar to modern Antarctica. The fact that it instead produced forests with diverse dinosaur faunas is a measure of how dramatically different the global climate of the Cretaceous was from our own, and a reminder that the relationship between latitude and temperature is not fixed, but depends on the broader context of global climate, including the concentration of greenhouse gases in the atmosphere, the distribution of land and sea, and the patterns of ocean circulation. Number 11. The mammals begin. Amid all the drama of rifting continents and inland seas and polar forests, something smaller and quieter was also happening during the Cretaceous period on the Australian portion of Gondwana. The mammals were beginning. The earliest true mammals had appeared in the late Triassic period, evolving from the therapsid lineages that had survived the Great Dying. These first mammals were small, mostly nocturnal creatures, living in the ecological margins left over from the dinosaurs that dominated the day. For most of the Mesozoic era, mammals remained small and relatively inconspicuous, a diverse group of perhaps 200 to 300 species worldwide, but none of them achieving the ecological prominence or body sizes that would characterize the mammals of the Cenozoic. In Australia, the earliest mammal fossils date to the Cretaceous period. These early Australian mammals included representatives of several major groups, including the monotremes, the egg-laying mammals that today survive as the platypus and the echidnas, and possibly early marsupials or their ancestors. The discovery of these ancient mammals in Australian Cretaceous rocks has been a significant achievement of Australian paleontology, requiring enormous patience and skill because the fossils are often tiny, the isolated teeth and jaw fragments of creatures no larger than a mouse. The monotremes are of particular interest because they represent the most ancient surviving lineage of mammals. The platypus and the echidnas are the only living members of this group, and their distinctive biology, including egg-laying, the production of milk through skin pores rather than nipples, and, in the case of the platypus, electroreception through the remarkable bill, represents a branch of mammalian evolution that separated from the lineage leading to the other mammals very early in mammalian history. The ancestors of today's platypus were already present in Australia during the Cretaceous, before the continent achieved its final separation from Antarctica. This means that the monotreme lineage has been part of the Australian fauna for at least 100 million years, making it one of the most ancient continuous evolutionary lineages on the continent. The living platypus, swimming in Australian rivers and detecting its prey through electrical fields, is in some ways a living connection to the Cretaceous world. Marsupials, the other uniquely Australian mammal group, have a somewhat more complicated origin story. The earliest marsupials appear to have originated in South America or North America, and they reached Australia through the land connections that still existed between South America, Antarctica, and Australia during the Cretaceous and earliest Cenozoic. Once in Australia, in the isolation that followed the continent's final separation from Antarctica, the marsupials underwent an extraordinary diversification, filling ecological roles that on other continents were occupied by placental mammals. Number 12. The final separation. Of all the geological events in Australia's history, the one with the most profound consequences for the continent's subsequent biological evolution was the final separation of Australia from Antarctica, approximately 35 to 45 million years ago during the Eocene epoch. This separation was not sudden. The rifting between Australia and Antarctica had been developing since the Cretaceous, and ocean floor was being created along the developing ridge between them for tens of millions of years before the two continents finally lost contact. But the critical transition came when the separation became wide enough to allow a continuous circumpolar ocean current to develop, flowing around Antarctica without interruption, isolating the southern continent thermally, and driving the glaciation of Antarctica that continues to this day. The opening of the Tasman Sea between Australia and Antarctica also had profound effects on global ocean circulation patterns, which in turn influenced global climate. As Australia moved northward into warmer latitudes, and as Antarctica became isolated by the circumpolar current and began to glaciate, global climates cooled and dried, eventually producing the ice age cycles that characterize the Pleistocene and that continue today. For Australia, the final separation from Antarctica meant something specific and biological. The land connections that had allowed the exchange of species between Australia and other parts of Gondwana were severed. Australia became a biological island, separated from all other major landmasses by thousands of miles of open ocean. The creatures that were already in Australia, the marsupials, the monotremes, the ancient reptile and amphibian lineages, the early representatives of the bird groups, the diverse insect fauna, were now isolated, cut off from any external evolutionary influence except for the occasional chance dispersal across the ocean from Asia to the north. This isolation was the making of modern Australia's extraordinary biodiversity. In the absence of competition from the placental mammals that were diversifying so rapidly on the other continents, the marsupials of Australia were free to evolve into an astonishing variety of forms. The thylacine, now extinct, was a marsupial carnivore that convergently evolved remarkable similarities to a dog or wolf, filling the large predator niche. The wombat became a burrowing herbivore, the koala a specialized leaf eater, the kangaroos and wallabies a diverse group of grass and shrub grazers, the quolls small to medium predators, the numbat a specialized termite feeder. In isolation, the marsupials became a complete mammalian fauna unto themselves. As you drift towards sleep, imagine that final separation. Two continents, once joined, pulling apart across millions of years, opening a widening seaway between them. Cold ocean water rushing in to fill the gap. The circumpolar current beginning to flow, beginning its long isolation of Antarctica. And Australia, now free, beginning its long northward journey toward the equator, carrying with it its cargo of ancient life, its marsupials and monotremes and eucalypts and ancient rocks, heading into the future. Number 13, the rocks that remember. There is a particular quality to the Australian landscape that sets it apart from almost anywhere else on Earth, and that quality is extreme age. The ancient cratons of Western and Northern Australia have been geologically stable for so long that the normal processes of mountain building, which refresh and renew the surface of the land on other continents, have had very little effect on them for hundreds of millions of years. On younger, more tectonically active continents, the surface is constantly being renewed. Mountains are pushed up, eroded down, and pushed up again. The old rocks are buried under new ones, or subducted into the mantle, or metamorphosed beyond recognition. The geological record is fragmented and discontinuous. In Australia, the geological record is continuous in a way that is almost unique on Earth. The ancient cratons have been sitting at or near the surface for billions of years, steadily accumulating the sedimentary records of every sea that has washed over them, every river that has deposited its load across them, every landscape that is formed on top of them. The result is a rock record of extraordinary completeness and antiquity. The Pilbara Craton of Western Australia preserves some of the oldest intact landscape surfaces on Earth. The Hamersley Plateau, which sits on some of the oldest rocks in the world, has been shaped by erosion into its current form over such a long period that it represents a genuine ancient landscape, not a recently formed one. The Bungle Bungle Range of the Kimberley, with its extraordinary beehive domes of banded sandstone, is carved from rock that was deposited as sediment in an ancient river system roughly 360 million years ago. The surface of the Nullarbor Plain is one of the largest and flattest limestone surfaces on Earth, and it preserves the fossil record of the shallow sea that covered it roughly 15 to 20 million years ago with extraordinary completeness. Everywhere in Australia, the rocks speak of deep time in a way that is unusual on other continents. The landscape is, in a very real sense, a library of Earth history, with volumes stretching back to the beginning of the rock record itself. The challenge for those who wish to read this library is scale. The volumes are enormous, the type is written in mineral grains and fossil fragments rather than letters, and the shelving system is geological rather than alphabetical. But the record is there, waiting to be read, and what it tells us about Australia during Pangea and Gondwana is a story of extraordinary continuity. A landmass that has maintained its fundamental character through the most dramatic geological and climatic changes Earth has undergone in the past 4 billion years, always changing and never staying the same, but always, in some deep sense, recognizably itself. Number 14. Ancient oceans in the desert. Perhaps the most startling revelation that comes from reading the geological record of Australia is the frequency and depth of the seas that have covered what is now dry desert. The Australian interior, today one of the harshest and driest environments on Earth, has been covered by shallow ocean water multiple times over the past 500 million years, each submergence leaving behind distinctive layers of marine sediment that are now exposed at the surface or buried at varying depths beneath the desert floor. The Eromanga Basin, which underlies much of inland Queensland, New South Wales, South Australia, and the Northern Territory, was the floor of the inland Cretaceous Sea that we discussed earlier. The rocks of the Eromanga Basin record a complex history of marine sedimentation, river delta deposits, coastal environments, and deeper ocean conditions, all reflecting the changing relationship between sea level and the land surface over tens of millions of years. But the Cretaceous Sea was not the only ocean to cover the Australian interior. During the Ordovician period, roughly 470 million years ago, much of central Australia was covered by a warm, shallow sea that was home to an extraordinary diversity of marine invertebrates. The fossil record of this ancient Ordovician sea is preserved in the rocks of the Amadeus Basin in the Northern Territory, where the eroded remnants of limestone reefs and seafloor sediments tell the story of a tropical ocean that once existed in the very heart of the continent. In the Devonian period, between 420 and 360 million years ago, a series of shallow seas occupied portions of what is now Western and Central Australia, and these seas supported reef communities of remarkable diversity. The Devonian reef complexes of the Kimberley region in Western Australia, now exposed as the Napier and Oscar Ranges, are among the best preserved ancient reef systems in the world. These ancient reefs, built not by corals as modern reefs are, but by organisms called stromatoporoids and tabulate corals, are so well preserved in the landscape of the Kimberley that they can be identified from the air by the characteristic shapes they give to the ridgeline. Walking through the Kimberley today and looking at these ancient reef structures, you are looking at the skeleton of a tropical ocean that flourished 370 million years ago. The individual organisms that built the reef are long dead, their soft tissues gone to nothing, but the architectural structures they built, the hard calcium carbonate frameworks that gave the reef its shape and strength, survive as rock in the arid Australian landscape. The presence of these ancient marine sequences throughout the Australian interior reminds us that the concepts of land and sea, of continent and ocean, are not fixed but temporary. The same piece of rock that is now desert floor has been seafloor multiple times in its history, and may be seafloor again in the far future. The apparent permanence of the landscape we see around us is an illusion created by the brevity of human attention spans relative to geological time. Number 15. The Great Artesian Basin and its ancient waters. Beneath a vast area of inland Australia, covering approximately 22% of the continent and underlying parts of Queensland, New South Wales, South Australia, and the Northern Territory, lies one of the largest and deepest groundwater systems on Earth. The Great Artesian Basin contains water that fell as rain in the recharge zones along the Great Dividing Range in eastern Queensland and percolated down through the porous sandstone layers of the basin, moving westward through the rock at a rate of perhaps 1 to 5 meters per year. The travel time from recharge to the distant Western Artesian wells, where the water rises under its own pressure to the surface, is estimated to be between 5,000 and 2 million years. The water flowing from an artesian bore in remote South Australia today may have fallen as rain before the first Aboriginal Australians arrived on the continent, but the story of the Great Artesian Basin reaches much further back than even this extraordinary timescale. The basin itself, the geological structure that contains the water, was formed during the Jurassic and Cretaceous periods when the region was occupied by the vast inland seas we have discussed. The porous sandstone layers that now form the main water-bearing aquifers of the basin were originally deposited as sands in the shallow margins of these ancient seas, in river deltas and coastal environments. Over time, these sands were buried under subsequent sediment layers, compressed, and eventually cemented into sandstone, but they retained enough porosity to hold water. The overlying sedimentary layers that cap the Great Artesian Basin, creating the pressure that causes water to flow upward at artesian bores, were deposited in the deep waters of the Cretaceous Sea that covered the basin at its maximum extent. These fine-grained, relatively impermeable shales and mudstones act as a seal, preventing the water in the deeper sandstone layers from escaping to the surface except where the natural pressure is sufficient to force it through, or where boreholes provide an artificial pathway. The entire basin is therefore a preserved record of the transition from the open Cretaceous Sea to the enclosed and eventually dry interior that Australia's interior became as the continent moved northward and the inland seas retreated. The rocks record the history, and the water trapped within those rocks represents a connection to a wetter, cooler past that is now accessible only through the artesian bore. For the Aboriginal peoples who have lived in the interior of Australia for perhaps 65,000 years, the mound springs associated with the Great Artesian Basin have been places of immense importance. Where the artesian water reaches the surface naturally, it creates permanent water sources in otherwise waterless country. And around these springs, communities gathered, stories were told, and relationships between people and land were maintained over thousands of generations. The ancient geological history of the Great Artesian Basin is inseparable from the human history of the country it underlies. Number 16. Fire and Ice, the Permian Record. The Permian period in Australia left behind two contrasting records that together tell the story of a continent caught between glaciation and warming, between ice ages and the subsequent recovery of life. The glacial record of the Permian is preserved in distinctive rock types called diamictites and varved sediments that are found across much of southern Australia. Diamictites are rocks that contain a chaotic mixture of rock fragments of all sizes, from boulders to clay, embedded in a fine-grained matrix. This characteristic mixture is the product of glacial transport, where a glacier picks up rock material of all sizes and carries it along without the sorting by size that water transport produces. When the glacier melts or deposits its load, the result is this characteristic unsorted mix of grain sizes. Varved sediments are thin, alternating layers of coarse and fine sediment deposited in glacial lakes. Each pair of layers, one coarse and one fine, represents 1 year of sedimentation. The coarse layer deposited during the summer when meltwater flows carried more sediment into the lake, and the fine layer deposited during the winter when the lake surface froze and only the finest clay particles slowly settled from suspension. By counting the varves, geologists can sometimes determine how long a particular glacial lake existed, a kind of ancient clock preserved in stone. The Permian glacial record in Australia shows that glaciations were not continuous, but occurred in pulses, alternating with warmer periods when the ice retreated. This matches the global pattern of Permian glaciation, which is thought to have been driven by astronomical cycles similar to those that drive the Ice Age cycles of the Pleistocene, combined with the changing geography of Gondwana as it drifted across the South Polar region. Above the glacial deposits in the rock sequence, the warming record of the later Permian is written in the coals and dark mudstones of the Glossopteris-bearing formations. As the glaciers retreated and the climate warmed, swampy forests spread across the landscape, and the dark, organic-rich sediments that accumulated in these forests are preserved today as some of Australia's most economically important coal deposits. The transition from glacial diamictites to coal-bearing sequences can sometimes be observed in a single road-cutting or quarry face, where the pale grey unsorted glacial rock gives way upward to the dark layered sediments of the forest swamps. In that vertical transition of a few meters of rock, you are reading the story of a climatic transformation that took hundreds of thousands of years to complete. A shift from an ice-covered landscape to a lush forest, a shift that would eventually be reversed by the catastrophe of the Great Dying. Number 17, the mountains that were. Modern Australia is famously flat. The continent has the lowest average elevation of any landmass on Earth, and its highest peak, Mount Kosciuszko, at 2,028 meters, is modest by the standards of other continents. The impression is of a geologically quiet, stable, ancient place where mountains are worn down and not replaced. But this flatness is deceptive, or rather, it is the product of time, of hundreds of millions of years of erosion acting on mountain ranges that were once as high as the Himalayas are today. The ancient rocks of Australia preserve evidence of multiple periods of mountain building, each one producing ranges of impressive height and extent that have subsequently been reduced to their current modest remnants by the patient work of wind and water over geological time. The most ancient mountain building episode visible in the Australian rock record is the Proterozoic orogenies that shaped the cratons of Western and Central Australia. The Musgrave province in the heart of the continent, straddling the border of South Australia, Western Australia, and the Northern Territory, preserves the deeply eroded roots of a mountain range that may have been as high as the modern Himalayas when it was built, roughly 1 billion years ago. Today, the highest peaks of the Musgraves reach barely 1,800 meters, gentle ridges on the horizon of the flat surrounding plain, and they are composed of rocks that were once buried 30 kilometers beneath the surface of those ancient mountains. The Alice Springs orogeny, which affected a broad area of Central Australia between roughly 350 and 300 million years ago during the Devonian and Carboniferous periods, created another range of significant mountains. The McDonnell Ranges that now form such a distinctive feature of the landscape around Alice Springs are the eroded remnants of this ancient mountain building event, reduced from their original heights to the modest ridges and gorges we know today. The quartzite ridges of the West McDonnells, turning orange and purple in the afternoon light, are rock that was originally laid down as sand in an ancient shallow sea and then folded and compressed into mountains during this Devonian collision. The Lachlan Fold Belt of New South Wales and Victoria, and the broader Tasman orogenic system that parallels the eastern coast of Australia, are the product of a prolonged period of mountain building that lasted from the Cambrian through to the Carboniferous, spanning roughly 250 million years in total. During this time, multiple episodes of island arc collision, sedimentary basin formation and inversion, and granitic intrusion built up the foundations of eastern Australia. At their peak, the mountains produced by these events along the eastern margin of the continent may have been comparable in height to the modern Alps or Rockies, significant ranges that influenced weather patterns, created river systems, and provided habitats for the evolving ecosystems of the Paleozoic era. Today, they survive as the Great Dividing Range, the low ridge of hills and tablelands that runs parallel to the eastern coast from Cape York to Victoria, and whose maximum elevation barely exceeds 2,000 meters. The erosion of these ancient mountains has produced something of enormous value. The sedimentary basins that border the Great Dividing Range on both sides, basins filled with the sediment eroded from the ancient highlands, and within those basins, the resource wealth that has defined so much of modern Australian history. The coal deposits of the Bowen and Sydney basins, the gold that was concentrated by ancient river systems, the lead, zinc, and silver of Broken Hill, all of these resources are, in some sense, the product of the slow erosion of ancient mountains. Number 18. The drifting continent, speed and direction. Australia's separation from Antarctica and its subsequent northward journey is one of the fastest continental drift events in the geological record. After the final separation around 35 to 45 million years ago, Australia began moving northward at a rate that, while imperceptible on any human timescale, is geologically remarkable. Today, Australia moves northward at approximately 3 to 4 centimeters per year, which is fast by the standards of plate tectonics. Over millions of years, this adds up to hundreds of kilometers of movement. In the 65 million years since the end of the Cretaceous, Australia has moved roughly 2,500 kilometers northward from its position adjacent to Antarctica, carrying its cargo of ancient life into warmer and warmer latitudes. This northward movement has had profound consequences for the climate and ecology of the continent. As Australia moved from cool southern latitudes toward the tropics, its climate dried dramatically. The continental interior, which during the Cretaceous had been covered by a shallow inland sea and had supported forests along its margins, became progressively more arid. The grasslands and scrublands that now cover much of the interior are a relatively recent feature of the Australian landscape, having developed primarily in the last 10 to 15 million years as the continent moved into its current subtropical position and global climate cooled and dried. The aridification of Australia was not a simple or linear process. It was driven by multiple factors acting in concert. The northward movement of the continent into the subtropical high-pressure belt, the development of the strong Southern Ocean circulation that cut Australia off from any marine moisture sources to the south, the progressive development of the Himalayan rain shadow as the India-Asia collision pushed mountains higher, and the global cooling and drying trend of the late Cenozoic associated with the growth of Antarctic ice sheets. As Australia dried, the flora and fauna adapted, or were replaced by forms better suited to the new conditions. The wet forests that had covered much of the continent during its time in the high southern latitudes gradually retreated to the wetter margins of the continent, to the rainforest refugia of Queensland, the wet forests of southwestern Australia, and the cool temperate rainforests of Tasmania. In their place, the sclerophyll vegetation, the fire-adapted, nutrient-conserving, drought-tolerant ecosystems dominated by eucalypts and acacias, expanded to cover the bulk of the continent. The eucalypts, in particular, are a story of evolutionary triumph in the face of aridification. The genus Eucalyptus is almost entirely endemic to Australia, with only a handful of species naturally occurring in nearby New Guinea and Indonesia. With over 700 species ranging from tall forest trees to low-growing mallee shrubs, the eucalypts have evolved to occupy almost every ecological niche in the Australian landscape, from tropical rainforest margins to alpine snowfields, from coastal heathlands to desert margins. Their success is built on a suite of adaptations to fire, drought, and nutrient-poor soils that have made them the defining botanical element of the Australian landscape. Number 19, the story in the soil. The soils of Australia carry their own record of the continent's ancient history, and they tell a story that is in some ways as revealing as the rocks beneath them. Soils form through the interaction of rock, climate, water, biology, and time. The older the land surface, the more time soils have had to develop, and the more the original mineral nutrients have been leached out by rainfall and removed from the system. Australia, with the most ancient and stable land surface of any continent, has consequently the most ancient and nutrient-depleted soils of any continent. The red and yellow soils that cover much of the Australian interior are extraordinarily old and extraordinarily poor in the nutrients that plants and animals need. This nutrient poverty has shaped Australian ecology in fundamental ways. Plants growing in poor soils must invest heavily in strategies to acquire, conserve, and recycle the nutrients they need. The Australian flora has evolved an extraordinary array of adaptations for this purpose. The proteoid roots of Banksias and Grevilleas that can extract phosphorus from soils too poor for most other plants. The nitrogen-fixing associations of wattles with soil bacteria. The ability of many eucalypts to resprout rapidly from epicormic buds after fire, recycling the nutrients stored in the trunk and branches without waiting for new nutrients from the soil. The fauna, too, has adapted to the nutrient-poor environment. Many Australian animals eat plants or prey on animals that eat plants. And in a nutrient-poor ecosystem, food chains are generally shorter, and each link is more carefully budgeted than in richer environments. The koala, subsisting on a diet of eucalyptus leaves that is extraordinarily low in nutrition and high in toxic compounds, is an extreme example of an animal that has evolved to exploit a food resource that almost nothing else can use. The wombat, with its extraordinarily efficient digestion and low metabolic rate, is another example of an animal that has tuned its physiology to the demands of a nutrient-poor landscape. The ancient weathered soils of Australia are also a record of the Gondwana connections that we have discussed. Some of the distinctive soil types of Australia, particularly the ancient laterite soils that cap much of the ancient plateau surfaces of Western Australia, began forming during the Gondwana period when the climate of the region was wetter and warmer than it is today. These ancient soils, formed tens of millions of years ago under conditions very different from the present, are now exposed at the surface, relic features of a landscape that no longer exists, preserved by the subsequent aridity that prevented their erosion. Number 20. Water in the ancient landscape. Water has always been central to the story of Australia, from the ancient oceans that covered its interior, to the rivers that carved its landscapes, to the groundwater systems that sustain life in its arid heart. The relationship between the Australian landscape and water is one of the defining themes of its geological and ecological history. The drainage patterns of Australia are ancient and, in places, extraordinarily old. The Murray-Darling Basin, the largest river system in Australia, drains a vast area of southeastern Australia through a network of rivers that has been developing since at least the Eocene, roughly 50 million years ago. But the pattern of drainage in the basin, the way rivers flow toward the Murray and then westward to the Southern Ocean, reflects tectonic and topographic influences that are much older than the rivers themselves. Some of the rivers of the Australian interior follow courses that were established by drainage systems that existed during the Cretaceous, when the continental surface was wetter and the inland sea was retreating. These ancient river courses, sometimes called paleochannels, can be detected by remote sensing even where they are buried under younger sediments. their presence revealed by the distinctive patterns they produce in satellite imagery. The Cooper Creek system of Central Australia, which normally flows only after heavy rainfall and spends much of the time as a series of disconnected waterholes in a dry channel, follows a course that has been part of the Australian drainage pattern for millions of years. During the rare flood events that bring the channel to life, Cooper Creek can become a vast inland sea, spreading across hundreds of kilometers of flat floodplain to create temporary wetlands of extraordinary biological importance. These flood pulses, brief but intense, are the lifeblood of the arid interior, triggering breeding events in birds and fish and reptiles that have evolved to take advantage of the unpredictable bounty that the floods provide. The pattern of unpredictable episodic flooding interspersed with long droughts is itself a product of the geological history we have been exploring. The extreme flatness of the Australian interior, product of hundreds of millions of years of erosion without renewal, means that water spreads rather than concentrating, creating shallow, broad flood events that dissipate over enormous areas. The position of Australia in the subtropical high-pressure belt, product of its northward movement from the high southern latitudes, creates the climatic conditions for long droughts and episodic intense rainfall. And the nutrient-poor soils mean that when rain does come, the response of the ecosystem is rapid and intense, as organisms that have evolved to wait out the dry times surge into activity. This ecology of feast and famine, of long patience and explosive response, is not accidental or incidental to the Australian character. It is the direct product of 4 billion years of geological history, written into the land itself and reflected in every organism that has evolved to live on it. Number 21. The Gondwana survivors. Among the most evocative biological reminders of Australia's Gondwana heritage are the living plants and animals that are shared between Australia and other former Gondwana landmasses, evidence of common ancestry dating back to the time before the southern supercontinent broke apart. The most famous of these are the southern beeches of the genus Nothofagus, which we mentioned earlier. These trees are found in southern South America, in New Zealand and New Guinea, and in the cool temperate rainforests of southeastern Australia and Tasmania. They are not closely related to the northern hemisphere beeches of the genus Fagus, despite their similar ecology and common name. The southern beeches are a genuinely Gondwanan group, whose ancestral forms were present in Gondwana before it broke apart, and whose descendants now survive on the fragments that once were joined. In the rainforests of Queensland, and particularly in the wet tropics region around Cairns, botanists have identified plant families and genera that are ancient relics of the Gondwana flora, surviving in the refuge of the tropical rainforest, while the rest of the continent dried and changed around them. Some of these plants belong to families that are also found in South America and Africa, their distribution inexplicable except as a legacy of their time in Gondwana. The Queensland kauri, the bunya pine, the ancient cycads of the Atherton tablelands. All of these are survivors from an earlier world, living fossils that connect the modern Australian landscape to its ancient southern heritage. The animals, too, carry Gondwana connections. The lungfish of Queensland's Mary and Burnett rivers is one of the most ancient surviving vertebrate lineages on Earth, a fish that can breathe air as well as extract oxygen from water through its gills. The Queensland lungfish is the sole remaining representative in Australia of a group that was diverse and widespread across Gondwana during the Mesozoic era, and its closest living relatives are found in Africa and South America. Like the plants, the lungfish distribution tells the story of a once unified southern world. The freshwater crayfish and the freshwater mussels of Australia show similar Gondwana distributions, with closely related species found in South America and indicating common ancestry from Gondwana. The velvet worms, soft-bodied invertebrates that hunt in the moist leaf litter of forests, are found across the former Gondwana landmasses and represent another ancient lineage that has been carried to its current distribution by the slow drift of the continents. These Gondwana survivors are more than scientific curiosities. They are living connections to a deep past, biological time capsules that have preserved the genetic and morphological legacy of an ancient world within the ecology of the modern one. When you see a southern beech in a Tasmanian rainforest or a lungfish in a Queensland river, you are looking at an organism whose lineage has been part of the southern world for 100 million years or more, an unbroken thread connecting the present to the Mesozoic and beyond. Number 22. The sky over ancient Australia. We have spent a great deal of this journey on the ground, among the rocks and rivers and ancient forests. But there is another dimension to the story of Australia during Pangea and Gondwana, and it is the sky above. The atmosphere of ancient Australia was dramatically different from the atmosphere we breathe today. During the Permian period, the oxygen content of the atmosphere fluctuated significantly, with some estimates suggesting it reached as high as 35% during the Carboniferous, compared to the approximately 21% of today. This elevated oxygen level had significant consequences for the organisms that lived in it, potentially allowing insects to grow to sizes far larger than anything alive today, because insect breathing depends on passive diffusion of oxygen through tubes in the body, and higher oxygen concentrations allow these systems to supply larger bodies. The carbon dioxide concentration in the Permian atmosphere was also very different from today. During the glacial phases of the Permian, carbon dioxide levels were relatively low, reflecting the cold conditions. During the warmer intervals between glaciations, carbon dioxide levels rose. The extraordinary warmth of the Cretaceous world, which allowed forests to grow at the poles and dinosaurs to live in Antarctic latitudes, was driven in part by carbon dioxide concentrations that may have been several times higher than today's already elevated levels. The sky over ancient Australia would have looked different in another way as well. The Earth's rotation has been gradually slowing over billions of years due to the tidal braking effect of the Moon. During the Devonian period, roughly 400 million years ago, a day on Earth was approximately 21 or 22 hours long, meaning there were more days in a year than there are today. Corals from the Devonian, which lay down daily growth bands in their skeletons, show approximately 400 bands per year, confirming the faster rotation of the ancient Earth. The Moon was also closer to the Earth in the distant past, though by the time of Pangea, it had receded to something reasonably close to its current distance. A closer moon would have produced stronger tides, and the tidal patterns along the shores of ancient Australia would have been more extreme than today's. The stars and constellations visible from the Australian portion of Gondwana were different from those visible from Australia today, not because the stars themselves changed significantly on these timescales, but because the position of the continent on the globe has changed. Australia has moved from high southern latitudes, where different stars were visible in the night sky, to its current subtropical position. The southern pole star, which appears fixed in the sky from the current position of Australia, would have pointed to a different location when Australia was further south. Number 23. The ice that carved. We have touched several times on the glaciations that affected Australia during the Permian period, when it was positioned near the South Pole within Gondwana. But it is worth taking a deeper look at the evidence for these glaciations and what they tell us about the landscape of ancient Australia. The Permian glaciation of Australia was part of the largest glaciation of the past 500 million years, a glacial event that affected all of Gondwana and left its mark on rocks across every continent that was part of the southern supercontinent. Geologists call this event the Late Paleozoic Ice Age, and it is thought to have lasted in various forms from roughly 340 million to approximately 260 million years ago, a duration of 80 million years that dwarfs any glaciation of the more recent past. During the peak of this glaciation, ice sheets covered vast areas of Gondwana, reaching from the South Pole outward into latitudes that today are subtropical or even tropical. Evidence for the glaciation has been found in rocks from South America, Africa, India, Antarctica, and Australia. All former members of Gondwana, and the consistency of the evidence across these now separated continents is one of the most powerful proofs of continental drift ever assembled. In Australia, the glacial deposits are most clearly preserved in South Australia, New South Wales, and Victoria. The Bacchus Marsh Formation in Victoria contains striated and faceted boulders that were clearly polished and scratched by glacial action, and the diamictite layers in which they are embedded show the characteristic structure of a glacial till. The Parakilna Formation in South Australia contains similar evidence of glacial action, as do many other Permian sequences across southern Australia. The glaciated landscapes of Permian Australia would have been austere and dramatic. Ice sheets, kilometers thick in places, pressing down on the ancient rock of the cratons, grinding and abrading the surface beneath them. At the margins of the ice, outwash plains covered with glacial debris, dissected by streams of meltwater running away from the ice front. Glacial lakes, dammed by moraines or by the ice itself, accumulating the fine silts that would become varved sediments. And beyond the ice margin, a periglacial landscape of permafrost and tundra, cold and treeless and windswept. The transition from this glacial world to the warming world of the late Permian was one of the most dramatic climate changes in Australian history before the modern period. As the ice retreated, the landscape was first colonized by pioneer plant communities adapted to cold and barren conditions. then gradually replaced by the more complex Glossopteris-dominated forests that would characterize the warmer Permian and provide the material for Australia's coal deposits. Number 24. The end of the Mesozoic and what came after. The end of the Mesozoic era, 66 million years ago, was defined by one of the most dramatic events in Earth history, the impact of a large asteroid or comet in what is now the Yucatan Peninsula of Mexico, combined with the enormous volcanic eruptions of the Deccan Traps in what is now India. This combined catastrophe, known as the Cretaceous-Paleogene extinction event, or sometimes still the KPG boundary, killed the non-avian dinosaurs, along with approximately 3/4 of all species on Earth at the time. Australia at the time of this extinction was still attached to Antarctica, and the particular biological communities of the Australian portion of Gondwana were profoundly affected by the extinction event. The non-avian dinosaurs that had been the dominant large animals of the Cretaceous were eliminated. The marine communities of the inland sea were devastated, and those seas were already retreating as global sea level fell in the final stages of the Cretaceous. In the aftermath of the extinction, the small mammals that had been living in the ecological margins of the dinosaur-dominated Cretaceous world were suddenly presented with an enormous range of ecological opportunities. With the large dinosaur predators gone and the large plant eaters gone, the mammals could expand in size, diversify into new ecological roles, and begin the radiation that would eventually produce the extraordinary diversity of mammals we know today. This radiation happened differently on different continents. On the northern continents, placental mammals diversified rapidly, producing the diverse orders we know today: the rodents, the ungulates, the carnivores, the primates, the bats, and all the others. On Australia, still attached to Antarctica at the beginning of the Cenozoic, the marsupials underwent their own radiation, producing the diverse Australian marsupial fauna that would eventually include the kangaroos, wombats, possums, bandicoots, and carnivorous marsupials that characterize the modern fauna. The critical difference, as we have discussed, was isolation. When Australia finally separated from Antarctica in the Eocene, the marsupials had already diversified substantially, and the separation prevented the subsequent invasion of placental competitors that reshaped the faunas of other continents. Australia became, and has remained, the last stronghold of marsupial diversity, a living laboratory of mammalian evolution running on a different set of rules from the rest of the world. Number 25. The Aboriginal connection to deep time. The geological story we have been exploring spans billions of years. The Aboriginal Australian connection to the land spans a much shorter but still extraordinary period, at least 65,000 years of continuous occupation, making it the oldest continuous culture on Earth. But the Aboriginal relationship to the land is not merely long in duration, it is profound in depth and intimacy. Aboriginal Australians, whose ancestors arrived on the continent when it was already isolated and had been drifting northward for tens of millions of years, developed over those 65,000 years an extraordinarily detailed knowledge of every aspect of the Australian landscape, from the distribution of water sources to the locations of food plants, from the behavior of animals to the patterns of weather. This knowledge, passed down through thousands of generations in the form of story, song, ceremony, and relationship, includes within it the echo of geological events. The oral traditions of Aboriginal Australians contain accounts of rising sea levels, of volcanoes, of changes in the landscape that have been corroborated by geological evidence. The stories of the drowning of coastal land by rising sea levels, which we know from geological evidence occurred dramatically in the period from about 20,000 to 7,000 years ago, as the last ice age ended, are preserved in the traditions of coastal Aboriginal peoples around the continent, telling of a time when land that is now under the sea was inhabited and then inundated. The knowledge of springs, of permanent water sources in otherwise dry country, that has allowed Aboriginal Australians to live in what Europeans considered uninhabitable desert, reflects a deep understanding of the hydrological systems that we have been discussing. The mound springs of the Great Artesian Basin, where artesian water reaches the surface, were known to Aboriginal peoples as sacred and vital places, and their significance is encoded in story and ceremony that connects the physical reality of the water to the broader network of meaning that ties people to country. The Aboriginal relationship to the ancient landscape of Australia is a reminder that deep time is not only the domain of geology and science. It is also the domain of story and memory and cultural knowledge, of the accumulated understanding of 65,000 years of careful, intimate attention to a land of extraordinary antiquity. Number 26, reading the minerals. The mineral wealth of Australia, one of the most resource-rich nations on Earth, is a direct product of the geological history we have been exploring. The ancient stable cratons of the west and north, undisturbed for billions of years, have preserved mineral deposits of extraordinary richness and diversity that would not have survived the geological recycling that occurs in more tectonically active regions. The iron ore deposits of the Pilbara in Western Australia, which make Australia one of the world's largest iron ore exporters, were formed approximately 2.5 billion years ago during a period called the Great Oxidation Event, when the first photosynthetic bacteria began producing oxygen in significant quantities, and that oxygen began to react with the iron dissolved in the ancient oceans. The result was the precipitation of vast quantities of iron oxide, which settled to the seafloor and accumulated in the distinctive banded iron formations that now crop out across the Pilbara. The gold deposits of Western Australia and the eastern states were formed by hydrothermal processes, hot, mineral-rich fluids circulating through the ancient crust, depositing gold and other metals in fractures and around rock contacts. Many of the gold deposits of the Kalgoorlie region and the Victorian goldfields were formed during ancient tectonic events, the collision and accretion processes that built the cratons and the Tasman orogenic belt. The gold that drew tens of thousands of prospectors to the Victorian and Western Australian goldfields in the 19th century was deposited by geological processes that operated hundreds of millions to billions of years ago. The copper, lead, zinc, and silver deposits of Broken Hill in New South Wales, one of the richest ore deposits ever discovered, were formed during the Proterozoic era, more than 1.5 billion years ago, by hydrothermal processes operating at great depths beneath the ancient crust. The Broken Hill ore body is itself a geological curiosity, a deposit of such antiquity and richness that it has attracted geological investigation since its discovery in the 19th century, and continues to yield new insights into the processes that concentrate metals in the Earth's crust. Australia's uranium deposits, another significant component of the country's mineral wealth, are found in rocks of varying ages, but are particularly significant in the ancient Proterozoic rocks of the Northern Territory and South Australia. The Olympic Dam deposit in South Australia, one of the largest known uranium deposits in the world, also contains significant quantities of copper, gold, and silver, and its formation involved processes that operated about 1.6 billion years ago, during the assembly of one of the supercontinents that preceded Gondwana. The mineral map of Australia is, in this sense, also a geological history of the continent, with different deposits marking different episodes in the 4 billion year story of the land. Reading that map with knowledge of the geological history behind it reveals a connection between the ancient processes of supercontinent assembly and dispersal, mountain building and erosion, ocean transgression and regression, and the material foundations of the modern industrial economy. Number 27. The shape of things to come. The story of Australia during Pangea and Gondwana is not just a story of the past, it is also a story of the future, because the geological processes that have shaped Australia over the past 4 billion years are still operating, and they will continue to operate in ways that will change the continent dramatically over the millions and billions of years to come. Australia is currently moving northward at approximately 3 to 4 centimeters per year, and this movement will eventually bring the continent into collision with Asia. The precise nature and timing of this collision is uncertain, because the details depend on the behavior of multiple tectonic plates and the changing dynamics of mantle convection beneath them. But geologists anticipate that within roughly 40 to 50 million years, the northern margin of Australia will have moved significantly closer to Asia, and the shallow seas and island arcs that currently occupy the space between Australia and the Asian mainland will have been largely squeezed out or subducted. The collision of Australia with Asia will produce mountain ranges along what is now the northern Australian margin, similar in some ways to the mountains currently being produced by the India-Asia collision that is building the Himalayas. These mountains, if and when they form, will completely transform the climate and drainage of northern Australia, creating barriers to atmospheric circulation and river drainage that do not currently exist. The east coast of Australia will also change. The subduction zones that currently operate to the east of the continent, swallowing oceanic crust into the Pacific, will continue to shape the eastern margin through volcanic activity and the possibility of new island arc collisions. The Great Dividing Range, already ancient and much eroded, will continue to be worn down by erosion, its sediments carried out to the continental shelf and into the deep ocean basins. In the very long term, hundreds of millions of years from now, Australia and the other current continents will have arranged and rearranged themselves into new configurations. Geologists have speculated about the future supercontinents that might form, with names like Marsia, Pangea, and Pangea Proxima, reflecting different models of how the current plates might eventually reassemble. In all of these scenarios, Australia will be part of the assembly, its ancient rocks contributing to the new configuration, its Proterozoic craton still stable and undeformed, at the cause of whatever new continent emerges from the next cycle of plate tectonics. Number 28, the language of rocks. Throughout this journey, we have been reading the language of rocks, the way that geologists decode the billions of years of Earth history that are written in stone. It is worth pausing to appreciate how remarkable this achievement of human knowledge actually is. The science of geology is, in one sense, an act of translation. The rocks do not come with labels explaining when they were formed, what processes created them, or what environments existed when the sediments were deposited. The information is encoded in the physical and chemical properties of the rock itself, in the mineralogy, the texture, the layering, the fossils, the isotopic composition, and the relationship to surrounding rock bodies. Geologists have developed, over 2 centuries of careful observation and experimentation, a set of tools for decoding this information that is quite extraordinary in its scope and precision. Radiometric dating, which uses the predictable decay rates of radioactive isotopes to determine the age of rock samples, can be applied to rocks ranging from a few thousand years old to more than 4 billion years old with remarkable precision. The zircon crystals from the Jack Hills of Western Australia that we mentioned at the beginning of this journey were dated using the uranium lid system, which uses the decay of uranium isotopes to lead isotopes over geological time to calculate when the crystals originally formed from a magma. Paleomagnetism uses the record of ancient magnetic field directions preserved in volcanic and some sedimentary rocks to determine the latitude at which those rocks were formed and to track the movement of the plates they now reside on. When magma solidifies, the magnetic minerals within it align with the direction of the Earth's magnetic field at that time, and this alignment is locked into the rock as it cools. By measuring the direction of this fossil magnetism in rocks of different ages, geologists can reconstruct the path that each piece of crust has taken through time. Paleoclimatology uses the fossil record, the isotopic composition of ancient carbonates, the distribution of rock types that form only in specific climates, and many other indicators to reconstruct the climate conditions of the geological past. The glacial deposits of the Permian, the tropical reef limestones of the Devonian, the coal swamps of the Carboniferous, all of these are climatic indicators as well as stratigraphic markers, telling us not just when a particular rock was formed, but also what the world was like when it was forming. The synthesis of all these different lines of evidence from different parts of the world, using different methods and covering different time intervals, is the work of generations of scientists. The picture of Australia's geological history that we have been exploring in this video is the result of that synthesis, a collective achievement of human knowledge that allows us to read the history of a continent written in a language billions of years old. Number 29, the deepest slough. We are approaching the end of this journey, and as we do, there is one more dimension of the story worth holding quietly in mind. The geological processes we have been describing are, by the standards of human life, almost incomprehensibly slow. Continental plates move at the speed of a growing fingernail, a few centimeters per year at most. Mountain ranges rise at perhaps a millimeter per year, at their most rapid. Sedimentary basins fill at rates measured in fractions of a millimeter per year in the deep ocean, perhaps a few millimeters per year in more energetic coastal environments. To produce the geological history of Australia that we have been exploring, this slowness has been multiplied by time on an extraordinary scale. The 3.5 billion year old rocks of the Pilbara were deposited when the Earth was less than 1 billion years old. The Permian glaciations that covered the Australian portion of Gondwana in ice concluded 250 million years ago. The separation of Australia from Antarctica, the event that set the continent on its current biological trajectory, concluded roughly 40 million years ago. There is something deeply quieting about these timescales. They dwarf not just individual human lives, but the entirety of human history. The earliest cities, built about 5,000 years ago in Mesopotamia and the Indus Valley, are separated from us by roughly 1/10,000th of the time that separates us from the final separation of Australia and Antarctica. The appearance of anatomically modern humans, perhaps 300,000 years ago, is separated from the Permian glaciation by a factor of nearly 1,000. Against these timescales, the concerns of any particular day or week or decade become very small, not meaningless, because human experience and human meaning do not require geological validation, but small in the way that a grain of sand is small on a beach, part of something larger and slower, and more patient than any individual can fully comprehend. Let that slowness settle into you now. Let the geological time of the Australian story be a kind of weight that holds you gently where you are. Press lightly into your bed or your chair, grounded in the present moment by the weight of 4 billion years of rock beneath you. Number 30, arriving in the ancient land. And now, as this journey through deep time draws toward its close, let the weight of all those years settle gently around you like a blanket. 4 billion years. 4 billion revolutions of the Earth around the sun. 4 billion years of rock building and eroding, of seas advancing and retreating, of continents assembling and breaking apart. 4 billion years of life evolving, diversifying, going extinct, and evolving again. And through all of that time, the piece of rock that is Australia has been there, changing constantly and remaining itself, accumulating the experiences of geological time like a diary written in stone. The Permian ice sheets are gone now, melted back into oceans that have since evaporated or drained away. The Cretaceous sea that once covered the interior of Australia is gone, its creatures fossilized in the rock of the Eromanga Basin, its water locked in the deep aquifers of the Great Artesian Basin, or long since evaporated into the sky. The polar forests of the early Cretaceous are gone, their descendants surviving in the small pockets of cool temperate rainforest in Tasmania and on the ranges of Victoria. The ancient mountains that once stood where the red plains of the interior now spread are gone, worn to their roots and then to nothing, their sediments dispersed across the continental shelf and into the deep ocean. But in a deeper sense, nothing is really gone. The atoms that made the Permian glaciers are still somewhere in the world, cycling through the atmosphere and ocean and rock just as they have always done. The molecules that built the Glossopteris forests are dispersed through the soil and the atmosphere, part of the continuous cycle of carbon and water and mineral that makes up the Earth's living envelope. The atoms of the ancient mountain ranges are now in the sedimentary rock of the basins and on the continental shelves and in the deep sea sediments, rearranged but not destroyed. The land of Australia, or the land you're thinking about tonight, is made of the same atoms that have been cycling through the Earth's systems for 4 billion years. Some of those atoms have been part of living organisms many times over, incorporated into bacteria and algae and Glossopteris trees, and Permian reptiles and Cretaceous dinosaurs, and Eocene marsupials before they arrived in their current configuration. Some of them were part of the ancient ocean before they were part of the land. Some of them arrived from space, delivered by the meteorites that have been falling on Earth since before the planet was fully formed. You are, in a real sense, continuous with all of this. The atoms of your body are borrowed from the same great cycling pool of matter that has made everything else that has ever existed on Earth. You are temporarily organized into the form of a person, listening to the story of an ancient continent. But the atoms themselves have been doing this kind of work for billions of years, and they will continue to do it long after any particular organization of them ceases. This is not a thought to provoke anxiety. It is a thought to provoke wonder. And perhaps, as you listen to it late at night or in the quiet hour before sleep comes, a thought that might make the concerns of any particular day feel proportionate to their actual significance in the vastness of geological time. The ancient rocks of Australia have seen ice ages and fire ages, mass extinctions and evolutionary radiations, the rise and fall of mountain ranges, and the advance and retreat of seas. They have endured 4 billion years of geological eventfulness with their fundamental character intact. In that deep geological sense, the land is stable and old and patient beyond anything human experience can easily comprehend. Let that stability ground you. Let the patience of the ancient rock be a kind of permission to rest, to release the urgency of the day, to sink into the slow rhythm of geological time where everything that needs to happen will happen in its own time, measured not in hours or days, but in the quiet accumulation of millions of years. Australia was here before us, and it will be here after us, continuing its slow drift northward into an ocean that is itself slowly being reshaped by the movement of plates beneath it. The story we have been telling tonight is not finished. It is only pausing, as you pause now, in the long middle of an ongoing process that has no end we can yet foresee. Sleep well. The land keeps its vigil. If stories like this are what you come here for, subscribe. The next one is already waiting. End of script number 31. The Cambrian explosion and the first animals of the ancient sea. long before Australia was covered in Glossopteris forests or polar dinosaur faunas. Before even the first land plants had colonized the bare rock of the ancient cratons, the shallow seas around the edges of the Proto-Australian landmass were the site of one of the most remarkable biological events in Earth history, the Cambrian explosion, which occurred approximately 540 million years ago, was the sudden and dramatic appearance in the fossil record of nearly all the major animal body plans that exist today. In the space of perhaps 20 to 25 million years, a geological eye blink, the world's oceans went from being dominated by simple microbial mats and a few enigmatic multicellular organisms to teeming with a bewildering diversity of complex, mobile, predatory animals with eyes and claws and shells and legs. The causal causes of the Cambrian explosion are still debated among scientists. Possible factors include a rise in atmospheric oxygen levels that made more energetic lifestyles possible, changes in ocean chemistry that made it easier for animals to build hard shells, changes in the structure of ecological communities triggered by the evolution of the first predators, and perhaps the reorganization of gene regulatory networks that open new evolutionary possibilities for body plan development. Whatever the causes, the Cambrian seas around Australia were among the most productive environments in the world during this extraordinary biological transition. The rocks of the Flinders Ranges in South Australia contain fossil beds of ediacaran organisms, the strange soft-bodied creatures that preceded the Cambrian animals, and that left their impressions in the ancient seafloor sediments of what was then a shallow tropical sea. These ediacaran fossils, some of the oldest complex multicellular organisms in the world, are found in the pound quartzite and related formations of the Flinders Ranges, and they give us a window into the world just before the Cambrian explosion transformed it. In the Cambrian itself, Australian rocks contain remarkable fossil beds. The Emu Bay Shale of Kangaroo Island in South Australia, deposited approximately 520 million years ago in what was then a shallow marine environment near the equator, contains some of the most beautifully preserved Cambrian fossils in the world. The remarkable preservation of soft tissues in the Emu Bay Shale, unusual for rocks of this age, has allowed paleontologists to describe the anatomy of Cambrian animals in extraordinary detail, from the structure of their eyes to the arrangement of their internal organs. The creatures found in the Emu Bay Shale would have been utterly alien to modern eyes. Anomalocaris, a large predatory animal with grasping appendages and complex compound eyes, was one of the apex predators of the Cambrian Ocean. Trilobites, those iconic three-lobed arthropods that are among the most common Cambrian fossils worldwide, crawled across the seafloor in enormous numbers. Worm-like creatures and small shelly organisms of uncertain affinity filled the ecological niches that later animals would occupy in very different forms. These Cambrian creatures were not yet Australian in any meaningful biological sense, because there was no concept of Australia as a distinct biological region for hundreds of millions of years. They were simply the inhabitants of a portion of the ancient seafloor that happened to be, in geological terms, in the vicinity of what would eventually become the Australian continent. But the rock that now forms their fossil tomb is Australian rock, and the story of their existence is part of the deep history of the land. Number 32. The Ordovician Sea and its reef builders. Following the Cambrian, the Ordovician period brought new developments to the seas around the Proto-Australian landmass. The Ordovician, lasting from approximately 485 to 444 million years ago, was a time of extraordinary marine biodiversity, sometimes called the Great Ordovician Biodiversification Event, during which the diversity of marine animal life tripled or quadrupled compared to the Cambrian. The shallow seas of Ordovician Australia were home to a diverse marine community that included brachiopods, the shell-bearing filter feeders that would dominate the seafloor for the next 200 million years. Graptolites, colonial organisms that floated in the water column, and are now among the most useful index fossils for dating rocks of this age. Echinoderms, the relatives of modern sea stars and sea urchins, which were diverse and abundant, and the first coral reefs, built by organisms called tabulate and rugose corals, whose descendants would eventually build the Great Barrier Reef. The Ordovician period ended with one of the largest mass extinctions in the history of life, triggered by a rapid glaciation event as the Gondwana supercontinent drifted over the South Pole and large ice sheets developed. The glaciation lowered sea level dramatically, draining the shallow epicontinental seas that had been so productive for Ordovician marine life, and the combination of habitat loss and cooling killed a very large proportion of all marine species. For the Australian portion of Gondwana, this Ordovician extinction left a distinctive mark in the rock record, a boundary between the diverse Ordovician marine sequences below and the impoverished early Silurian sequences above. The recovery from the Ordovician extinction took several million years, and the Silurian period that followed saw the gradual rebuilding of marine diversity and the development of new kinds of ecological communities. The Silurian period is also notable for the appearance of the first vascular land plants, simple rootless plants related to modern liverworts and mosses, which began to colonize the bare rocky surfaces of the land during this time. The colonization of the land by plants was one of the most transformative events in Earth history, fundamentally changing the way weathering worked, the chemistry of rivers and soils, and the nature of the terrestrial environment. For the Proto-Australian landmass, this plant colonization was the beginning of a process that would eventually produce the extraordinary floral diversity we see today. Number 33. The Devonian Revolution. The Devonian period, from approximately 419 to 359 million years ago, is sometimes called the Age of Fishes because of the extraordinary diversification of fish that occurred during this time. But the Devonian was also the period of the first forests, the first amphibians, the first insects, and the first terrestrial vertebrates, making it one of the most revolutionary periods in the history of life. For the Australian portion of Gondwana, the Devonian is particularly significant because of the extraordinary reef systems that developed along its margins, the Devonian reef complexes of the Kimberley that we mentioned earlier. These reefs, built primarily by stromatoporoids and tabulate corals in warm, shallow tropical seas, were among the most productive marine environments of their time, comparable in biological richness to modern coral reef systems. The Canning Basin of Western Australia preserves one of the most complete records of a Devonian reef system anywhere in the world. The reef sequence in the Canning Basin records the development of a reef complex from its initial colonization of a carbonate shelf through its mature phase, characterized by complex reef structures with distinct back reef, reef crest, and forereef environments, to its eventual demise during the late Devonian mass extinction that ended the period. The Devonian also saw the development in Australia of the first freshwater fish faunas, diverse communities of fish adapted to life in rivers and lakes rather than the sea. Australia's Devonian freshwater fish assemblages, found in the red sandstone sequences of Victoria and New South Wales, are among the most diverse and best preserved in the world. These ancient fish, some of them armored in heavy bony plates, as protection against the large predatory fish of the time, were the distant ancestors of the fish that would eventually colonize every freshwater environment on Earth. On land, the Devonian saw the spread of forests across the previously bare continents. These early forests, dominated by tree-like lycopsids and early ferns, were very different from the forests we know today, but they were nevertheless genuine forests, with tall trees creating a shaded forest floor and a diverse understory of smaller plants. The spread of these forests had profound effects on the global carbon cycle, drawing down large amounts of carbon dioxide from the atmosphere and contributing to a long-term cooling trend. The Devonian ended with another significant mass extinction, the late Devonian extinction event, which killed a very large proportion of marine species, particularly reef-building organisms. The cause of this extinction is still debated, but it appears to have been related to a combination of factors including global cooling, ocean anoxia, and possibly extraterrestrial impacts. The reef systems of the Kimberley, which had been so productive through the Devonian, were essentially destroyed by this extinction, and their skeletal remains are now preserved as the ancient limestone ridges of the Kimberley landscape. Number 34. The Carboniferous and the Coal Forests. The Carboniferous period, from approximately 359 to 299 million years ago, is named for the coal deposits that were formed during this time in the warm, humid forests of the tropical and subtropical zones of Pangea. But as we have discussed, the Australian portion of Gondwana was not in the warm tropics during the Carboniferous. It was positioned at high southern latitudes, experiencing cold conditions that would develop into the full glaciation of the Permian. Nevertheless, the Carboniferous left its mark on the Australian geological record. The period is represented in Australia primarily by marine sequences in the west and south, deposited in the cool, shallow seas that bordered the continent at this time, and by terrestrial sequences in the east that record the developing landscape of the Proto-Australian landmass. The Carboniferous marine sequences of Australia contain a distinctive fossil fauna adapted to the cool, high-latitude conditions of the time. Unlike the warm water faunas of the tropical Carboniferous seas of the northern parts of Pangaea, the Australian Carboniferous marine fauna was composed of cold-adapted organisms, and their distinctive character is part of the evidence that allows geologists to reconstruct the paleogeographic position of Australia during this period. The terrestrial record of the Australian Carboniferous is less complete, but it gives hints of the landscape that existed at high southern latitudes during this time. Some plant fossils have been found that suggest the development of early cold-tolerant plant communities in the higher parts of the Proto-Australian landmass, pioneer vegetation occupying the margins of the glaciated terrain. These cold-adapted plant communities were the forerunners of the Glossopteris flora that would dominate the Australian Permian. The Carboniferous also saw important developments in the evolution of the terrestrial vertebrates. The amniotes, the group of vertebrates whose eggs could develop on land without needing to return to water, diversified during the Carboniferous and began to occupy terrestrial environments more fully than any vertebrates had before. The amniotes would eventually split into two major lineages, the sauropsids, which gave rise to the reptiles and birds, and the synapsids, which gave rise to the therapsids and eventually the mammals. Both of these lineages were diversifying during the Carboniferous, and their descendants would eventually become the dominant land animals of Australia. Number 35. The life that survived. One of the most remarkable aspects of the geological history of Australia is the extraordinary continuity of some biological lineages through the vast stretches of time we have been exploring. While many groups have come and gone, appearing in the fossil record during one period and disappearing during an extinction event or simply being outcompeted by new arrivals, others have persisted with remarkable fidelity across hundreds of millions of years. The stromatolites are perhaps the most extraordinary example. Stromatolites are layered structures built by communities of photosynthetic bacteria called cyanobacteria, which trap sediment and build up characteristic dome-shaped or columnar structures in shallow water. They are found in the fossil record from as far back as 3.5 billion years ago, making them among the oldest known examples of life on Earth. And they are still alive today in a few locations around the world where conditions are sufficiently inhospitable to prevent the grazing animals that would otherwise destroy them from establishing themselves. One of the most famous living stromatolite sites in the world is Hamelin Pool in Shark Bay, Western Australia. Here, in a hypersaline lagoon where the high salt content prevents most animals from surviving, stromatolites still grow on the seafloor, building their characteristic layered structures, just as their ancestors did 3.5 billion years ago. The Hamelin Pool stromatolites are living representatives of an ecosystem type that was dominant on Earth for the first 2 billion years of life's history, before the evolution of animals capable of grazing on them caused their decline. The nautilus, a shelled cephalopod mollusk, is another remarkable survivor from deep time. The ancestor of the modern nautilus was present in the Cambrian seas of ancient Australia, and the group has persisted largely unchanged in its basic body plan through 500 million years of evolution and at least 3 major mass extinctions. The coiled shell, the numerous tentacles, the jet propulsion mechanism, all of these characteristics were present in nautiluses of the Ordovician and Devonian, as they are in the nautiluses that swim in the tropical Pacific today. The horseshoe crabs are another ancient lineage found in the fossil record from the Ordovician and persisting to the present with little change in their fundamental body plan. The modern horseshoe crabs, which come ashore on certain beaches to breed in enormous numbers, are creatures of almost unchanged architecture from animals that walked the seafloor of ancient Gondwana seas 400 million years ago. These living fossils, as they are sometimes called, are not evolutionarily stagnant. Genetic studies consistently show that they have been evolving at the molecular level throughout their history. But the ecological niches they occupy and the general solutions to the problems of survival that they have adopted have proven so effective that the basic design has not needed to change substantially. In their persistence, they connect the modern world to the deepest past, living links in the chain of biological history that stretches back to the beginning of life on Earth. Number 36. The ancient climate of the deep interior. One of the enduring mysteries of Australian geology is the question of what the climate of the deep interior was like during the various geological periods we have been discussing, and how that climate shaped the landscape and the biological communities of the time. The modern Australian interior is one of the most arid environments on Earth. Large areas receive less than 250 millimeters of rain per year, and some areas receive far less than that. The dry heart of the continent, the vast erg of sand dunes and bare rock that covers much of the center, is the product of the aridification that has been developing over the past 10 to 15 million years as Australia moved into its current subtropical position. But the interior was not always so dry. During the Cretaceous, when the inland sea covered much of the center of the continent, the climate of the surrounding land was significantly wetter than today. The coastal margins of the inland sea supported forests and diverse terrestrial ecosystems, and the rivers that drained into the sea carried substantial loads of sediment and organic material. During the early Cenozoic, after the separation from Antarctica, but before the full development of modern aridification, the Australian interior supported forests and wetlands that would be unrecognizable today. Fossil evidence from Riversley in Queensland and Naracoorte in South Australia, among other sites, reveals a Miocene Australia with a much wetter interior, where rainforests extended far into the center of the continent, rivers flowed more reliably, and diverse communities of large mammals, birds, and reptiles occupied ecological niches that no longer exist in the modern dry interior. The Miocene megafauna of Australia included giant wombats, enormous kangaroos, and a diversity of large marsupial browsers and grazers that are now extinct. These animals occupied a continent that, while recognizably Australian in its fundamental character, was dramatically different from the modern landscape. The transition from this wet Miocene world to the dry modern world was one of the most significant ecological transformations in Australian history, driving many species to extinction and forcing the survivors to evolve adaptations for an increasingly harsh environment. Number 37. The ocean that surrounds. Australia is often thought of as a continent defined by its land, by the vast interior, the ancient rock, the unique flora and fauna. But Australia is also defined by its ocean, by the extraordinary seas that surround it on all sides, and that have shaped its history as profoundly as any geological event on the land itself. The Southern Ocean, which surrounds Antarctica and laps against the southern coast of Australia, is the most recently formed ocean on Earth. Before Australia separated from Antarctica, the Southern Ocean did not exist as a continuous body of water. The separation of the two continents, by creating a pathway for water to flow completely around Antarctica, brought the Southern Ocean into existence and gave it the extraordinary power that it wields in global climate today. The Antarctic Circumpolar Current, which flows from west to east around Antarctica without interruption, is the largest ocean current on Earth by volume. It transports more water than all the world's rivers combined, and it plays a critical role in global ocean circulation by mixing surface and deep waters and distributing heat around the planet. The development of this current, following the separation of Australia from Antarctica, had profound effects on global climate, contributing to the cooling and glaciation of Antarctica and to the long-term drying trend that has characterized the past 30 to 40 million years. The Indian Ocean, which lies to the west of Australia, has also played a fundamental role in shaping the continent's history. The monsoon circulation that brings summer rains to northern Australia is driven by the temperature contrast between the heated land surface of Australia and the cooler Indian Ocean waters. And this monsoon is itself the product of the specific configuration of land and sea that exists in the tropical Indian Ocean. Changes in the configuration of land and sea as India moved northward and as the Tethys Ocean closed affected the monsoon circulation and influenced the climate of northern Australia throughout the Cenozoic. The Coral Sea, lying to the northeast of Australia, is the home of the Great Barrier Reef, the largest coral reef system on Earth and one of the most diverse marine ecosystems in the world. The Great Barrier Reef began forming roughly 25 million years ago as Australia moved northward into tropical latitudes, and the shallow shelf along its northeastern margin entered the warm waters where coral reef organisms can flourish. The reef that exists today is not the original Miocene reef, but the product of continuous reef building on the same general site, interrupted multiple times by sea level changes associated with the Pleistocene ice ages, which exposed the reef platform and killed the corals, and then rebuilt by the return of warm, shallow water as sea levels rose again. Number 38. The long night of the Antarctic separation. Let us return, one more time, to the moment of separation. The moment when Australia and Antarctica finally drifted far enough apart to allow the ocean to flow between them, ending the last land connection between the two continents and beginning the long isolation of Australia that would define its subsequent biological history. This moment was not a single point in time, The separation was a process, beginning with the first rifting of the lithosphere in the Cretaceous and continuing through the gradual widening of the seaway between the two continents over tens of millions of years. But there was a threshold, a point at which the seaway became deep enough and wide enough to allow a continuous ocean current to establish itself, and once that threshold was crossed, the consequences were irreversible on any timescale meaningful to life. For the organisms that lived on the Australian portion of the combined landmass, the separation was not a dramatic event felt in any immediate way. There was no great flood, no violent earthquake, no sudden change. The continents moved apart at their customary geological pace, and the expanding seaway was simply a gradually deepening body of water where before there had been shallow sea or land. But on the timescales of evolution, the effect was profound. The gene flow between the Australian and Antarctic faunas, already reduced as the climate of the high latitudes became increasingly inhospitable, eventually ceased entirely. Australian organisms were on their own. The marsupials that had arrived from South America through Antarctica would diversify without any external competition. The ancient monotremes would persist as the sole representatives of their lineage. The birds, which had diversified into many forms, would continue their evolution in isolation. The specific character of modern Australia, its biological uniqueness, its extraordinary endemism, its strange and beautiful peculiarity, is the direct product of this isolation. And that isolation has its roots in the geological event of continental separation, in the opening of a seaway between Australia and Antarctica that began as a rift in the crust and became, over millions of years, the Drake Passage of the South, the Southern Ocean, the circumpolar current that isolates Antarctica and regulates global climate to this day. When you think of Australian animals, the kangaroo bounding across red desert country, the platypus swimming in a cool mountain river, the echidna digging for insects in the sandy soil, you are thinking of the products of this long isolation. You are thinking of evolutionary experiments conducted in a biological laboratory defined by ancient rock, warm shallow seas, and the opening of a seaway that changed the world. Number 39, The Stars That Watched. There is one more dimension of the Australian deep time story worth pausing over before we close, and it is the one that is perhaps most easily forgotten in a geological narrative focused on rock and ocean and extinction. Throughout all of the billions of years we have been exploring, throughout the Proterozoic and the Cambrian and the Devonian and the Cretaceous and all the rest, the Australian piece of the Earth's crust was not alone in the universe. It existed within the solar system, orbiting the same sun that we orbit today. Above it, the same sky spread out, populated by the same stars, following the same paths through the night. Aboriginal Australians have maintained astronomical traditions for at least 65,000 years, making them the inheritors of the oldest astronomical tradition on Earth. The specific star lore and sky knowledge of Aboriginal peoples varies across different groups and regions of the continent, but some common themes emerge across many traditions. The Milky Way is read not just as a band of light, but as a landscape of features, with dark patches within the Milky Way identified as animals and significant places in the sky country. The dark cloud constellations of Aboriginal astronomy, which identify figures in the dark nebulae of the Milky Way rather than in the patterns of stars, are a sophisticated and distinctive approach to the night sky that has no precise parallel in any other astronomical tradition. The practical uses of astronomical knowledge for Aboriginal peoples included navigation, timing of seasonal events such as the availability of particular foods, and the organization of ceremonial life. The return of the Pleiades star cluster to visibility in the pre-dawn sky in June signals the season for collecting various kinds of food in some Aboriginal traditions. The position of the Southern Cross is used to determine direction. The appearance and disappearance of particular stars marks the passage of the seasons and the appropriate times for ceremony and ceremony preparation. This astronomical knowledge, like the geological knowledge encoded in stories of ancient floods and volcanoes, is a form of deep time awareness specific to human culture. It is knowledge accumulated over tens of thousands of years of careful observation, passed down through generations in story and ceremony, and refined through long practice in one of the clearest night skies in the world. It connects the present to the past in a different way than geology, but with no less depth or precision. Number 40, The Gift of Ancient Land. And now, as this exploration of deep time reaches its final moments, let us hold together all the threads we have followed and see what they weave. Australia during Pangea was not Australia at all, not in any meaningful sense. It was a portion of a southern supercontinent called Gondwana, itself embedded within the greater Pangea, positioned near the South Pole, covered in ice sheets and sparse vegetation, inhabited by therapsids and early seed ferns, and the last complex communities before the Great Dying would reset the entire story of life. But the atoms that made those ice sheets, that made the Glossopteris leaves and the therapsid bones, are still here. They have been rearranged countless times since then, passing through Triassic forests and Jurassic seas, and Cretaceous polar dinosaurs and Eocene marsupials, and 10,000 generations of every creature that has lived and died on this ancient landmass. They are in the red soil of the interior, and the limestone of the Nullarbor, and the iron ore of the Pilbara, and the coal beneath the Bowen Basin. They are in the leaves of the eucalypts, and the fur of the wombats, and the scales of the ancient lungfish. And they are in us, whoever we are, wherever we are listening from. The atoms of our bodies are part of the same great cycle, the same 4 billion year story of matter being organized and reorganized by the processes of geology and chemistry and biology. We are temporary expressions of the same ancient material that has always been here, always changing, always arriving at new configurations. There is something deeply restful about that thought, if you let it settle. We are not separate from the deep history of the land. We are continuous with it, made of it, part of the same story that began with the formation of the oldest zircon crystals in the Jack Hills of Western Australia 4.4 billion years ago, and that has not yet found its ending. Let that continuity be with you now, as you breathe slowly in and out, as the day's concerns grow quieter and smaller, as the long patience of the ancient rock becomes the rhythm beneath your breath. You are part of an old story. The land has been here through ice ages and extinctions and the slow drift of continents, and it will be here, continuing and changing, long after any particular arrangement of atoms has dissolved and reformed into something new. Sleep now in the deep time of the ancient southern land. The story continues without urgency. The continents are still moving. The atoms are still cycling. And somewhere in the deep rock beneath the red Australian desert, the oldest terrestrial crystals on Earth are still quietly doing what they have always done, which is simply to exist, patient and ancient and undisturbed, in the deep, slow foundation of the world. If this is the kind of story that helps you rest, subscribe. There are more where this came from, and they are all waiting for you. End of script. Number 41. The breath of the old continent. There is something that geologists sometimes call the breathing of the Earth, the rhythmic rise and fall of sea levels over millions and tens of millions of years, driven by changes in the rate of seafloor spreading, the growth and melting of ice caps, and the slow shifting of water between ocean basins as the continents move and the ocean floor changes shape. Australia has experienced the full range of this geological breathing over the course of its long history. Seas have advanced inland across the flat continental surface during periods of high global sea level, flooding the interior basins with shallow warm water and creating the epicontinental seas we have discussed. And seas have retreated during periods of lower sea level, draining those inland waters and exposing the seafloor as new land, new habitat for the creatures of the terrestrial world. During the height of the last glacial maximum, approximately 20,000 years ago, when enormous ice sheets covered much of the northern hemisphere and global sea levels were roughly 120 meters lower than today, the Australian continental shelf was exposed as dry land. The continental shelf around northern Australia, which today is shallow and submerged, was then part of the land surface, connecting Australia more closely to New Guinea and creating a larger landmass called Sahul. The people who were the ancestors of today's Aboriginal Australians lived on this expanded continent, on land that is now beneath the Arafura Sea and the Timor Sea and the Gulf of Carpentaria. Their archaeological sites, their hearths and tool scatters and food remains, are buried now underwater, invisible to conventional archaeology, but preserved in the sediments on the sea floor, waiting for the technology and the will to find them. As the last ice age ended and sea levels rose, that land was gradually inundated. The rising sea advanced inland at a rate that was perceptible on the timescale of a human life, perhaps a meter or two per year in some areas, flooding river valleys and coastal plains, and ultimately creating the coastlines we know today. The oral traditions of coastal Aboriginal peoples, as we have discussed, preserve memories of this inundation, stories of a time when the sea was far away that are now corroborated by geological evidence. This rhythm of advance and retreat, of land and sea exchanging their territories in response to the deep breath of the Earth's climate system, is one of the most characteristic features of the Australian geological story. It is a story of constant change that looks like permanence from any human vantage point, but reveals itself as perpetual motion when viewed across geological time. Number 42, the desert that was a sea. The Simpson Desert, stretching across parts of Queensland, the Northern Territory, and South Australia, is one of the most arid and remote places on Earth. Its parallel sand dunes, some of them over 100 kilometers long and 30 meters high, are the product of wind-driven sediment transport operating over thousands of years in one of the driest climates on the continent. But the sand that forms those dunes is not recently deposited. It is ancient, derived ultimately from the erosion of rocks that were themselves formed in various geological periods, transported by rivers and winds through multiple cycles of deposition and reworking over millions of years. And beneath the sand, the bedrock of the Simpson Desert tells a different story. A story of ancient seas and rivers and the steady accumulation of sediment in a landscape that has been through many incarnations before arriving at its current desert character. The Lake Eyre Basin, of which the Simpson Desert forms a part, is an endorheic basin, a basin with no outlet to the sea. Rivers flow into it from surrounding highlands, but have no way out, either evaporating or sinking into the ground. At the center of the basin, Lake Eyre, now known by its traditional name Kadithanda, sits at approximately 15 meters below sea level, the lowest point in Australia. During the Pleistocene, when global climates were cooler and wetter, the Lake Eyre Basin held significantly more water than it does today. The lake itself was much larger, and the rivers that drained into it were more powerful and more reliable. The fossil record from around the lake basin, including the extraordinary assemblages at Terrari and other sites, reveals a Pleistocene Australia with large permanent lakes and diverse wetland communities, very different from the occasional and ephemeral floods that characterize the modern basin. Further back in time, during the Cretaceous, the Lake Eyre Basin was at the bottom of the great inland sea we have discussed, covered by tens or hundreds of meters of saltwater. The marine fossils found in the rock beneath the desert, the ammonites and plesiosaurs and mosasaurs, whose remains are occasionally exposed by erosion, are a reminder that this desert was once an ocean, and that the concept of desert and ocean as fixed properties of a landscape is an illusion created by the shortness of human memory. Number 43. The ancient fire. Fire is perhaps the most characteristic feature of the Australian landscape, the element that has shaped the ecology of the continent more profoundly than any other over the past tens of millions of years. The fire-adapted vegetation of Australia, the eucalypts with their flammable oils and their capacity for rapid respreading after fire, the acacias and banksias and heath plants with their heat-triggered seed release mechanisms, all of this is the product of a long evolutionary history of adapting to a fire-prone landscape. The geological history of Australian fire extends back at least to the Miocene, when the drying of the continental interior and the expansion of eucalypt-dominated vegetation began to create landscapes that were highly flammable during dry periods. Fossil charcoal, preserved in sedimentary sequences of Miocene and Pliocene age, tells the story of ancient fires burning across a landscape that was already developing the fire-prone character we recognize today. But fire in Australia may have an even deeper history than the geological record directly reveals. The eucalypts evolved as a group much earlier than the Miocene, and their distinctive chemistry, characterized by the volatile aromatic oils that make them so flammable, suggests that fire may have been a significant selective pressure throughout their evolutionary history. The extraordinary diversity of eucalypt species, with their remarkable range of adaptations to different fire regimes, suggests not a recent response to fire, but a long evolutionary dialogue with it. When the ancestors of today's Aboriginal Australians arrived on the continent at least 65,000 years ago, they brought with them the technology of fire and the cultural knowledge of how to use it. Over the subsequent millennia, Aboriginal peoples used fire extensively as a land management tool, burning vegetation on a regular and deliberate cycle that maintained the mosaic of different vegetation types and ages that supports the greatest diversity of wildlife. This practice, often called fire stick farming by researchers, was so pervasive and so consistent over such a long period that it effectively became part of the ecological process of the continent. And many Australian ecosystems are now so adapted to regular human-managed fire that the cessation of that management causes its own ecological disruptions. The story of fire in Australia is therefore a story that connects geology and biology and culture, connecting the deep evolutionary history of flammable vegetation to the long cultural history of deliberate burning, connecting the ancient Miocene landscapes where fire first became a dominant ecological force to the present day, where the management of fire remains one of the most pressing environmental challenges on the continent. Number 44. The silence between the stories. Between each of the geological periods we have been exploring, between the Ordovician and the Silurian, between the Devonian and the Carboniferous, between the Permian and the Triassic, there are boundaries in the rock record where the transition from one world to the next is marked by mass extinction, by the sudden disappearance of much of the life that had been accumulating over the previous period. We have discussed the Great Dying at the Permian-Triassic boundary, the largest of all the mass extinctions in the geological record. But there were others. The late Ordovician extinction that ended the extraordinary marine diversity of that period, the late Devonian extinction that destroyed the reef systems of the Kimberley, and much else besides, the end Triassic extinction that cleared the way for the great radiation of the dinosaurs, and the Capage extinction 66 million years ago that ended the age of the dinosaurs and opened the way for the mammals. In the Australian rock record, each of these extinctions is visible as a change in the fossil assemblages preserved in the rock. Above each extinction boundary, different organisms are present, or familiar organisms are dramatically reduced in diversity, reflecting the rebuilding of biological communities from the survivors of the catastrophe. The extinctions are silences in the story, moments when the constant accumulation of life's diversity was interrupted and had to begin again. But the silences are also full of significance. The mass extinctions, terrible as they were for the organisms that lived through them, were also the opening moves in new chapters of evolutionary history. Without the Great Dying, the dinosaurs might never have achieved their dominance. Without the KPG extinction, the mammals might never have diversified beyond the small nocturnal insectivores they were during the Mesozoic. Without the late Ordovician extinction, the fish and the amphibians that followed might never have had the ecological space to develop. The silences between the stories are part of the story. The extinctions are not interruptions in the history of life, but turning points. Moments when the direction of evolutionary history changed and new possibilities opened. The Australia we know, with its marsupials and its monotremes and its extraordinary endemic flora, is the product not just of the millions of years of continuous evolution, but also of the extinction events that cleared the way for new beginnings. Number 45. The memory in the bone. Among the most evocative physical legacies of Australia's ancient history are the megafauna fossils, the remains of the enormous animals that lived on the continent until relatively recently, and that represent the last chapter of the long story of Australian mammalian evolution before the arrival of humans. The Australian megafauna included creatures that seem almost mythological in scale. Diprotodon, a wombat-like creature the size of a rhinoceros, the largest marsupial ever to have lived. Procoptodon, a giant short-faced kangaroo that stood 2 meters tall and could not hop in the manner of modern kangaroos. Thylacoleo, the marsupial lion, a powerful predator whose skull structure suggests a bite force comparable to that of a modern lion. Dromornis statoni, the heaviest bird ever to have lived, a flightless creature that stood nearly 3 meters tall and weighed perhaps 500 kilograms. These animals lived on a continent that was geologically ancient and biologically distinctive, and they were the products of tens of millions of years of marsupial evolution and isolation. They occupied ecological niches that on other continents were filled by very different kinds of animals: large herbivores, apex predators, heavy rooters and grazers. And they were remarkably successful, surviving multiple climatic fluctuations and habitat changes over millions of years, before disappearing in what appears to have been a geologically brief period, sometime between about 50,000 and 40,000 years ago. The cause of the megafauna extinction is one of the most debated questions in Australian paleontology. Two main hypotheses have been proposed and contested for decades: that the megafauna were hunted to extinction by the newly arrived humans, and that climatic changes associated with the transition from the last glacial maximum to the current interglacial disrupted their food sources and habitats beyond their capacity to adapt. The current balance of evidence suggests that both factors probably played a role, with different species and different regions showing different patterns, and with the overall conclusion that the combination of a new predator with novel hunting strategies and a shifting climate may have been more than most megafaunal species could withstand. The bones of the megafauna are found in caves, in dried lake sediments, in the fossil record of sites across the continent. Each bone is a reminder of what was here and is now gone, a record of the last few million years of Australian biological history before the most recent transformation of the continent's ecology. Number 46. Coming to rest in the ancient. We have traveled a long way tonight, across 4 billion years of geological time, from the formation of the oldest crystals in the Jack Hills to the megafauna of the Pleistocene and the human history that followed. We have visited ancient oceans and polar forests, mass extinctions and evolutionary radiations, the assembling and breaking of supercontinents. And all of this has been in service of a single question. What was Australia like during Pangea? The answer, as we have seen, is complicated by the fact that Australia during Pangea was not yet Australia. It was a portion of Gondwana, itself a portion of Pangea, positioned in the high southern latitudes and experiencing conditions radically different from the warm, dry continent we know today. The land was icy in the south and temperate in the north, covered in the distinctive Glossopteris flora of the southern supercontinent, inhabited by therapsid mammal-like reptiles bordered by ancient seas. But the story does not end with Pangaea, or even with Gondwana. The story continues through the Triassic breakup and the Jurassic inland seas, and the Cretaceous polar forests and the Eocene separation from Antarctica, right up to the present moment, where Australia is still moving northward, still carrying its ancient rocks and its unique biological cargo into the future. This is what deep time means, not the distance of the past from the present, but the continuity of the process that connects them. The rock beneath Australia is old, but it is not finished. The evolution of Australian life is ancient, but it is still happening. The movement of the continent is slow, but it is ongoing. Nothing in the story of Australia is over. Everything is still in motion, still changing, still writing the next chapter in a story that began 4 billion years ago and has not yet found its ending. Let that openness carry you into sleep. The story is not finished. The land is not done. And you, resting now in whatever corner of the world you occupy, are part of the ongoing story of matter organizing itself in interesting ways on a planet that has been doing this for a very long time. Rest in the ancient, sleep in the deep, slow patience of the old rock. And when you wake, the continent will still be drifting northward, 3 or 4 centimeters closer to Asia than it was today, patient and unhurried, continuing the longest journey in the history of the southern world. If these explorations of deep time and ancient Earth are what bring you here, subscribe. There is so much more of the story to tell, and it will all be waiting for you, just like the land, patient and slow and ancient, whenever you are ready to listen again. End of script. Number 47. The deep grammar of the land. Geologists who work in the field develop something that might be called geological intuition, a trained sense of what a landscape is saying through its shapes and colors and textures. A geologist walking across the Australian outback reads the land the way a fluent reader reads a page, automatically, without effort, deriving meaning from details that a non-specialist would simply see as rock and dust. The color of the soil tells them something about its age and the chemical processes that have shaped it. The dark red of ancient weathered laterite is different from the pale orange of more recently exposed sandstone, which is different again from the grey-brown of alluvial plains or the white of salt lakes. Each color is a piece of information, a clue to the history of the particular patch of ground. The shapes of hills and ridges speak of the rock types beneath them. Hard, resistant rocks, those that have survived the weathering that eroded the surrounding softer material, stand as ridges and inselbergs above the plains. The orientation of ridges tells of the direction of ancient tectonic stresses that folded the rocks. The roundness or angularity of boulders tells of the distance and mechanism of their transport. The distribution of plant communities reflects both the geology and the hydrology of the landscape. Certain plants are indicators of particular soil types, which in turn reflect underlying geology. The presence of mulga, the acacia scrubland of arid Australia, is a reliable indicator of red sandy soils over certain sedimentary sequences. The presence of spinifex, the hard-leafed grass that dominates much of the desert, indicates sandy soils with good drainage over various rock types. For Aboriginal Australians, this reading of the land goes even deeper, encompassing not just the geological and ecological information visible on the surface, but also the cultural and spiritual dimensions encoded in story and song. The landscape is read simultaneously at multiple levels, as a physical environment, as a historical record, as a cultural text, and as a living entity with which people maintain relationships of obligation and reciprocity. Both of these ways of reading the land, the geological and the cultural, are forms of deep attention, of the patient accumulation of knowledge about a specific place over time. Both are ways of listening to what the land has to say about its own history, and both lead ultimately to the same recognition, that the land is old beyond easy comprehension, that its history dwarfs any individual human lifespan or even any human civilization, and that to inhabit it is to participate in something immeasurably larger and slower than any immediate concern or comfort. Number 48. What the light touches now. And so, as we arrive at the end of this long journey through time, let us come back, gently and slowly, to the present. The light that touches the Australian landscape today is the same light that has touched it for 4 billion years, the light of the same sun that has been burning for 5 billion years, and will continue to burn for another 5 billion or so. That light falls on red desert and green forest and blue coastal sea without preference or distinction, illuminating the ancient and the recent alike. The ancient rocks of the Pilbara, which have been in their current position relative to each other for 3 billion years, are lit by the same light as the new suburbs of Perth, built within the last generation. The coal seams of the Bowen Basin, compressed from Permian forest over 250 million years, are lit by the same light as the modern mining equipment that extracts them. The Great Barrier Reef, built on the skeleton of the ancient seafloor over 25 million years, is lit by the same light as the tourist boats that carry visitors out to see it. Everything in the landscape, ancient and recent, simple and complex, geological and biological and cultural, exists simultaneously in the same present moment, illuminated by the same indifferent and sustaining light. The deep past is not behind us, separated by the arrow of time. It is here now in the physical substance of the landscape, in the DNA of every living organism, in the stories carried by the cultural traditions of the oldest continuous cultures on Earth. Deep time is not somewhere we need to travel to reach. We are already in it. We have always been in it. The geological past is not an abstraction or a number too large to grasp. It is the rock beneath our feet, the soil our food grows in, the atoms of our bodies. It is the present moment experienced in its full dimensionality, as the latest instant in a story 4 billion years in the making. Let that present settle around you now like the last light of a long day, warm and golden and full of the satisfaction of a journey completed. You have traveled through deep time tonight, from the oldest crystals to the present, from ice sheets to polar forests to inland seas to the red desert of the modern continent. You have heard the story of a land that has always been changing and has always, in its essential character, been itself. And now it is time to rest. The land will continue its slow work without you. The atoms will continue their cycling. The continent will continue its drift. The ancient rocks will continue to be ancient, carrying the memory of 4 billion years in every grain and crystal, patient and silent in the deep foundation of the world. Sleep now. The ancient southern land holds vigil, and in the morning, when you wake, the story will still be there, continuing as it always has, as it always will. If you're here for stories like this, subscribe. There are more of them, all of them old, all of them waiting, all of them telling the story of how the world we live in came to be the way it is. End of script. Number 49, The Patience of Stone. There is a particular kind of patience that belongs to stone and to the slow processes that work upon it. And it is a patience so different in scale from anything in human experience that it can feel when you truly try to comprehend it, like encountering a different dimension of time itself. We measure our lives in years, occasionally in decades, rarely in generations. Our sense of deep past extends comfortably to perhaps a few centuries. The span of historical memory, and with effort to a few thousand years, the reach of the oldest continuous oral traditions. Beyond that, the past becomes abstract, a matter of numbers and facts rather than felt duration. But stone knows another kind of time. The granite of the Pilbara has been cooling and crystallizing and slowly eroding for more than 3 billion years. In that time, the solar system has completed roughly 12 orbits of the Milky Way galaxy. The Earth has rotated on its axis more than 1 trillion times. The oceans have evaporated and refilled from volcanic sources multiple times. Life has gone from simple bacteria to complex multicellular organisms to the extraordinary diversity of the modern world. And through all of that, the stone has simply been stone, changing slowly in response to the forces acting on it, carrying in its mineral structure the record of everything that has happened to it, patient in a way that has no analog in any living experience. When we speak of the patience of ancient rock, we are speaking of something that is not really patience at all, because patience implies the experience of waiting, and rock does not experience anything. But there is something in the endurance of old stone, in its persistence through change and catastrophe, and the slow work of time, that feels like a quality we might learn from. Not the absence of experience, but the acceptance of process, the willingness to be shaped by forces larger than oneself without resistance or complaint, changing completely over millions of years while remaining fundamentally what it is. The ancient rocks of Australia have been shaped by Proterozoic mountain belts and Paleozoic seas and Mesozoic forests and Cenozoic aridification. They have been buried and uplifted, flooded and dried, heated and cooled, scraped by glaciers and smoothed by rivers. And they are still here, still recognizable in their fundamental character, still telling the story of everything they have been through to anyone patient enough to listen. There is something deeply reassuring about that persistence. Whatever the disruptions of any particular day or decade or century, the old rock continues, the story goes on, the atom cycle, and the continent, patient and ancient and unhurried, continues its slow drift into whatever future the movement of plates and the evolution of life will bring. Rest in that persistence now. Let the deep time of the ancient continent be a ground beneath your thoughts, solid and vast and patient, supporting everything that rises and falls above it without effort or resistance. The land has been here through much more than any of us will ever face, and it will be here long after any particular concern has dissolved into the past. Sleep now in the patience of the old stone land. Sleep in the deep grammar of the ancient earth. Sleep in the 4 billion years of quiet accumulation that made the ground beneath you what it is. And let the morning come in its own time, unhurried, as all things in geological time are unhurried, patient and sure and full of the next chapter of the longest story ever told. End of script. Number 50, the final drift. One last thought before this journey ends, and before the quiet of deep time settles fully around you, in approximately 10 million years. Give or take the considerable uncertainties of geological prediction, the northern coast of Australia will have moved roughly 300 to 400 kilometers closer to Asia. The Torres Strait, which today separates Australia from New Guinea by about 150 kilometers of shallow sea, will have changed. The shallow Arafura Sea that fills the space between Australia and the island of Timor will have shrunk. New islands may have risen along the developing collision zone, and the ancient landscape of northern Australia will have acquired the early signs of a new mountain belt along its margin. The plants and animals that inhabit the continent will have changed too, not dramatically in 10 million years, not by the standards of the deep time changes we have been exploring tonight, but measurably, discernibly. New species will have evolved from the populations of today. Some of today's species will have gone extinct. The distribution of ecosystems will have shifted as the climate continues to respond to the changing geometry of land and sea. The eucalypts will still be there, probably, in some form or another, because they are a robust and adaptable group. But the specific assemblage of 700-odd species will be different, shaped by 10 million more years of natural selection and chance. None of us will be there to see it. The span of a single human life is to 10 million years what a single heartbeat is to a human life, a small and specific event embedded in a much larger rhythm. But the continent will be there, and it will be recognizably Australian, carrying the same ancient cratonic rocks, the same broad flat interior, the same orientation toward the equator, the same general character that it has had since it separated from Antarctica 40 million years ago. And in its rocks will be the record of everything that happened before that point in the future, including the present moment, including this night, including you resting wherever you're resting, and listening to the story of how Australia came to be. Not you specifically, not in any recoverable detail, but the general pattern of the present moment will be there, encoded in the sediments being deposited right now in the rivers and coastal waters of the continent, in the fossils being formed right now from the organisms dying in the soil and the sea, in the chemical changes being written right now into the rock by weathering and diagenesis, and all the other slow processes of geology. The present moment is always becoming the geological record. The now that we inhabit is the future past, the ancient time that someone or something a million years hence might read in the rock and wonder about. This thought, too, is a kind of gift, a reminder that we are not standing outside geological time, observing it from some secure and timeless vantage point, but participating in it, adding our moment to the long accumulation, as every moment that has come before has added itself to the story. Sleep now in your moment in geological time. Sleep in the comfort of the ongoing story. Sleep in the certainty that the ancient land will still be here tomorrow, still moving, still accumulating, still carrying the memory of everything it has been through into whatever comes next. And if stories like this one, stories that reach back to the beginning and stretch forward toward the horizon of deep future time, are what you come here for, then subscribe. The world is old, and there is so much of its story left to tell. Rest well, the continent drifts, the story continues, and deep beneath the red Australian desert, in the oldest rock on the surface of the planet, the 4 billion year memory of the land sleeps quietly, as it always has, as it always will.